All right, welcome to day 4, Lognormal Distribution. So as I mentioned yesterday at the end, my goal here is to try to help you with without a lot of formulas, right? So I want to try to relate everything back to the normal distribution. And I feel like if you just remember a few things from the normal, you will be unstoppable. Okay, so hopefully I'll be successful with this. I'm trying it. So let's see what this happens with you. So I just remember when I studied for this one, like I kind of felt like there's these formulas. I wasn't really like that clear what was happening. I was able to like do some of the basic problems, but then if the problems got a little harder, I was just lost. So if that's the way that you felt, then hopefully this seminar will be really beneficial to you. Okay, so let's start with a review of the normal distribution, just some of the notations that we'll use. It's pretty common, but just some of the ones that we'll use and some of the properties that are going to be important. And the most important thing on this page will be what we talk about down here. So, all right, but in general, so here's sort of the notation that we're always going to use. If X is normally distributed with the mean and the variance. So sometimes you wonder, like, why did they put the variance, not standard deviation? Well, it just is what it is. It's the notation, but it's because probability people love variance, but stats people love standard deviation. So we're not stats people, we're probability people. So we use the variance, and variance is just easier to work with. Standard deviation is just kind of like much more cumbersome. Like, it's like the square root of a bunch of sums of squares, and it's just like, oh, it's just ugly. So for us, the variance is the preference. Okay, and they're going to use this like little, tilde here. You can think of that as like an equals sign. It's going to behave a lot like an equals. So I might even write equals sometimes. It's okay, or maybe even all the time. Don't worry so much about that. It's just like a formality. So we're more interested in just being able to get the results and being able to use it without having to be super formal. Okay, but notice how we're actually going to use a capital N with 2 parameters. Okay, so keep that in mind. We'll come back to that in a minute. All right, now to be able to do these, you totally remember the first thing you have to do is you have to standardize. And so if you have some sort of X, if you subtract the mean over the standard deviation, that gives us a Z value, capital Z. And Z is a standard normal. Standard normal just means mean of 0, variance or standard deviations of 1. And if we were to draw out the density curve, the density function, we don't really remember the density too much, but if we draw out the density function, we get this curve here, the bell curve. And so the thing is, with the density for the normal, you just can't integrate it. It's impossible, at least as far as anybody knows right now. You could try it. It's basically just trying to integrate e to the negative x squared. But if you try to integrate that, you just can't. It's not possible. So they have to use some sort of table or computer or something to give you the probability values. And so that's what they're going to do. They're going to actually give you the probability that Z is less than or equal to a number, right? Both of those are the same for continuous. So, and that's just going to be what they call N of X. So keep in mind, we have capital N with 2 parameters and a capital N with 1 parameter. So totally different things. Capital N with 1 parameter down there, well, that is just the probability that X is less. This is like the capital F that we did back in probability exam. That's all the capital N is here with 1 value, is just the capital F for the standard normal, the Z value. So for me, anytime I see probability Z less than or equal to something, I'm going to immediately just say, oh, that's just N of this. And then that's where we're going to have to use the prometric calculator. We're going to need that a lot today. So if you want to just Google it, type in prometric normal calculator or something like that, and it's gonna give you something like this. So the prometric calculator, I think this is one from Coaching Actuaries, but whatever, it's the same thing. You might remember it. Just pull up one of these. We're going to need them today. Okay, but that is actually where you would type in the value for X and you get N of X probability. And if I had probability Z is greater than X, well, okay, so really, I guess what I'm looking for is sort of like the probability of the tail, but by the symmetry, that's really the same as the probability of that tail. So that's really just the same as N of negative X. So N of negative X there, which is great. So for me, whenever I see probability Z less than, I'm doing N of X. And whenever I see probability Z greater than, I'm going to do N of negative the X. And I'm just going to think about that and then just realize that these are just complements of each other. So n of X, oops, that's X, n of X is really just 1 minus n of negative X. All right, just complements. They're just, so you'll see that like n of negative D1 is just really 1 minus n of D1. We see that a lot. So, all right, now some of the essential properties that we're going to need, and it might seem weird to kind of write them like this, and hopefully we'll be able to explain this in a minute, but if I had just like some number plus a number times a normal distribution, well, what do we get? Well, it turns out that normal is like a really awesome distribution because it's super absorbent. So anytime I just like multiply a normal by a value, it remains normally distributed. And even if I added a number to it, it remains normally distributed. So this is actually going to be some normal distribution. I just need to know what is the new mean and variance. And so if I call this one like X, I could say, oh, what is the, oh, sorry, maybe I'll call this one X. So what is the expected value of this new thing? Okay, well, by expected values, it's super easy. It's just A plus B times the expected value of X. And I know the expected value of X, the mean of X is just the mu. So the mean of this new combination is just going to be A plus B mu. And if I wanted to know the variance of this new distribution, well, I know that, oh, adding something to a value, that doesn't change the variance. Do you know why, by the way? It's kind of an easy thing to talk about, but variance measures spread. So if I just kind of added a value to everything, I would just be shifting it. And when I shift it, it doesn't change the spread. It just kind of, just shifts it over. So if I take a value and add it to everything, that's not going to change the spread. So the A kind of goes away, but anytime I pull a constant out, I have to square it out of the variance. So this is actually going to be B squared variance of X, which is actually just B squared and sigma squared. So B squared sigma squared. So that'll actually be the new variance of this new distribution, right? So nothing new. It's not really formulas we remember. You can kind of think of this as a little shortcut. And the way that I'm gonna kind of think of it here, we're not going to really be adding a lot, but we are going to be multiplying constants by a normal distribution. So I think about it like, okay, I'm gonna, once I can kind of distribute the B in, but I'm going to distribute it into the first one, but the square is going to be distributed into the second component there. So I'll kind of write it sort of like this. I'll put like a little square up there. So I'm going to distribute it in the B, but I'll kind of have to square it going into the second one. And then when I add the A, it's just going to add to the mean, not the variance. And we kind of see why. Okay. Now, what happens if I added two normal distributions? It's actually super nice, right? Again, normal is absorbent. So this is really just going to be one new normal distribution. Actually, I'll put it down here because it's going to be a little bit big. And the cool part is that, oh yeah, the expected value or the mean of the new distribution will just be the sum of the means of the other ones. So it's really just going to be mu1 plus mu2. And then the standard or the variance of the new distribution. So it's kind of like if I had the variance of X plus Y. So the variance of X plus Y is variance of X plus variance of Y plus 2 covariance of XY. Especially if they're not necessarily independent, which we're going to sometimes have, sometimes not. So we kind of want to know the more expanded version. So this is actually sigma 1 squared plus sigma 2 squared. Oh, and by the way, maybe we'll call that sigma 2 there. Sigma 2 squared, and then plus 2. Oh, yeah, please.
Is this equally weighted?
These are, yes. These are going to be equally weighted, yeah. And if they're not, I can kind of apply this first to get two equally weighted ones, and then I could get it. Yeah, good. So there's no coefficients here, like 2 of those and 3 of those or something. If I did have that, though, I could kind of multiply that in first and then do this after. Yeah, I hope that answers it. Yeah, a great question. Thanks, Joseph. Appreciate it. And then I'll have 2 covariants, but a lot of times they're not going to do covariants. They do the row. So it's actually 2 row sigma 1 sigma 2. So good. And then So that's just going to be nice. And so that's nice basically. And if they're independent, then I'm just going to have add the means, add the variances, and I'm good. So nice. All right, then what about this one here? I wrote it kind of in a funny way. Sorry about that, but so basically, but I want you to kind of think about it a certain way. So I wrote it like this. But if I wanted, if I had some sort of X here with a certain mean and a certain variance, then I want to know, well, how is it related to Z? Well, it's actually just this thing again, right? Because that's how X and Z are related, but I'm just going to work it the other way. So I'm going to move X, I'm going to solve for X basically, and I'm going to get X equals, well, Z times sigma, and then plus mu plus sigma Z. So notice how it's actually just going to be the mean plus, well, sigma, so standard deviation. Now, so I'd actually have to go square root of the variance times Z. Now, this would be good for things like percentiles. So I'll just kind of put that down here. This is going to be good for percentiles. So that includes the median. This is going to be a great thing for the median. Be a great thing for like confidence intervals, things like that, if they wanted you to find the confidence interval of a stock price in the future or something like that. So you could use this because that really is just, you know, percentiles there too. So, okay, but we're not going to really use it a lot, but I just wanted to show you that, yeah, it's actually just going to be the first parameter plus the square root of the second parameter times Z. Okay, but we'll come back to that. We'll talk about how to use that. And then expected value of E to a normal. Now, like I said, this is actually going to be the most important thing we talk about on this page, right? So the expected value of E to a normal. So we're going to have this kind of like saying, because we're going to use this over and over and over again, and it's going to open up so much to us. But the expected value of E to the normal is E to the first parameter plus 1/2 second parameter. So that's kind of how I want to remember it. This is probably the only thing that we'll actually have to memorize today if we don't know this. Okay, now, the reason why, by the way, and actually they give you this formula on their formula sheets, but we're just going to use it so much, we're not even going to pay attention to it. But this is actually related to the moment generating function. Do you remember, if X is normal, what the moment generating function was? Well, the moment generating function of a normal, mx of t, sorry, that's kind of sloppy, sorry, mx of t was e to the mu t plus 1/2 sigma squared t squared. And the actual definition of the moment generating function was expected value of e to the xt, or tx, or however you want to do it. It was expected value of e to the xt. So expected value of e to, in this case, a normal times t. And for us, we're just going to have t equals 1. And so that's where we just get mu plus 1/2 sigma squared. Okay, now it's a really surprise. It's like, if you're not really ready for it, it seems like such a surprise. It's real logical. It's okay. It's not really crazy, but it might just, maybe you might not have seen this before or thought about this before. But you know how in like all these formulas, we always have like a plus 1/2 sigma squared or minus 1/2 sigma squared or whatever. It's actually because of this. Like you might have wondered, it's like, why are we always subtracting a 1/2 sigma squared or adding a 1/2 sigma squared? What's the deal with that? And this is the reason. Okay, but it's real subtle. They don't really kind of tell you that, but we're going to use this more from a computational point of view. Anytime we say in our mind, oh, expected value of e to a normal, oh, okay, if that's the case, I'm going to think about this. It's just e to the first parameter plus 1/2 the second parameter. When I first started doing these, I just kind of thought like, oh, could I just do like expected value of the normal up there, and it's just like e to the mu or something, and I didn't really know. So, but I learned it's like, oh no, it's actually, this is the thing. You can't just take the expected value up to the exponent. You can do a lot with expected values, but you can't do some things. So you just have to be a little bit careful. So this is going to be super huge. This is going to be an important thing. So, all right, as we go now, the thing that we're going to want to do is we're going to want to make sure that we try to spot the normal distribution. That's our goal. So let's practice this a little bit. Okay, and then we'll get into log normal stuff in a minute. So we're still just talking about normal for now, but they say here, suppose that the log of x is normally distributed. Oh, and sorry, I should have probably said this too. I will probably just say log instead of natural log, kind of out of laziness, but really, you probably even seen this, like nobody really uses log base 10. So, so kind of like in higher math, anytime they say log, they really mean natural log. So I'll probably say that here. Please don't think that I'm saying like the log base 10. Some books even write log for natural log, so it's okay. It's just kind of a thing that they do later. I just want to mention that in case you kind of get confused, like, wait, which log 10 or natural log, or which one? So, and you can feel free to do that too. It kind of shows like sort of where you're at. Like, so, okay. But anyway, suppose that log X is normally distributed with mean of 1.5, standard deviation of 3. So what are we going to write here? Well, something is normally distributed with mean of 1.5 and standard deviation of 3. So I'm going to write 9 as the variance, just out of convention. You could put 3 and just kind of remember its standard deviation, but it's better to always be consistent. So we'll just keep it like that. And then what is normally distributed? They said log X is normally distributed. Okay, so log X is normally distributed. Okay, so if I talk about a normal distribution, if I'm going to subtract the mean over standard deviation, I have to start with this. I have to start with log X. I can't start with X. I got to start with log X, because that's the thing that's normally distributed, right? Okay, so then they said, okay, what about the probability then if they asked for probability that X is greater than 0.9? Well, you might be tempted to sort of like subtract the mean over standard deviation, but again, X is not normally distributed. Log X is normally distributed, but that's okay. It's actually a quick fix. I'm just going to go, just kind of put the natural log there first, log both sides. And now I can like subtract the mean over standard. Now I can standardize. So I'll write out this step. We won't really do this after this, but so now log X minus the mean over standard deviation is greater than log 0.9 minus the mean over standard deviation. And then this thing here, this actually becomes Z, the standard normal. So this is actually probability Z greater than, and then just compute out this right-hand side. So log 0.9 minus 1.5 over 3, and it gives me negative 0.53512. And so for me, it gets down to, okay, probability Z greater than. Oh, okay, so probability Z less than is the normal one. That's the typical one. That's the capital F, the cumulative distribution. This is PZ greater. Oh, okay, this is going to be N of negative then. So this is really just N of negative this number. So I guess N of positive 0.53512. All right, and now I just kind of plug that into the normal calculator. So feel free, just kind of, pull out this one and put in the 0.53512 for X. That's going to be a little hard for me, but I kind of already have these all finished here. So, so I got here 0.70372.
Okay, so why do we switch it to the positive and not the negative?
Okay, because it's probability Z greater than. So back down here, that's this. Whenever I've got probability Z greater than something, it's kind of like the complement. It's like 1 minus N of X. And you could have said that. Or we can just shortcut it and just go N of negative the number that I had. So the number I had itself was negative. It was negative 5.51. So I'm going to do N of negative that. So I'm going to go N of positive 0.53512. Yeah, great question. Please, any little things like that, please, don't feel bad or anything. Just please ask it. Okay, but it's actually going to go back to that, and we're going to have a lot of these examples. So, but yeah, it's just this property right here. And so you kind of remember, whenever you used capital F back in the exam P, there was kind of only 3 things that could happen. It was really the probability that, the variable is less than something, the variable is greater than something, or the variable was between 2 things. And so then you really just had like capital F of something, 1 minus capital F of something, or capital F minus capital F, right? That was like the 3 scenarios that we had back in the P exam. And it's the same thing here. That's really this capital N is really just like a capital F. So I'm really going to have just N of 1 minus N of, or just N of negative. That's equivalent. And then if it's the probability that Z is between two things, then I'll just do capital F minus capital F or capital N minus capital N, and I'll be able to do those. I got examples of that coming up too. Yeah, but great. Yeah, great. Please. Yes. Any questions that you have? Absolutely. Okay. But yeah, then I just got 0.7032372. All right, now what about expected value of X? So it's not 1.5. That would be the expected value of the natural log of X, right? So that would be, if they asked me for expected log X, that would be 1.5 because log X is naturally or normally distributed. But now I'm doing expected value of X. But actually the cool part is it's really quick. It's a quick thing because I can kind of think of this as like an equals up here. This log X is kind of like equals normal. So if I wanted just what X was, what would I have to do to both sides? And you're like, well, I got to undo the log. The way I do that is raise, e to both sides. So I'm just going to get X equals e to this normal. Right? So X is e to the normal. That's the same as log X is normal. Right? E both sides. And then if I wanted to do expected value of X, so that's expected value of e to the normal 1.5 and 9. And okay, well now expected value e to a normal, oh, easy, right? That's just going to be expected value e to a normal. That's just going to be e to the first parameter, 1.5 plus 1/2 second parameter, a 9. And this just gives me e to the 1.5 and 4.5 is e to the 6. Okay, the answer I don't really care so much about, but just the process here, where we're seeing that we're going to actually see a lot of e to the normals coming out of this because what we're describing here is the log normal distribution. Okay. What about expected value of X squared? Okay, well, so I'm actually going to go back to this. And what if I wanted X squared? What would I do? Well, I would square both sides. So I'd kind of square that side. But the big thing is what happens here over on the right side. But it's actually kind of easier than you think. Because whenever I have like something raised to an exponent and then to another exponent, that's kind of like an X to the 5th squared. It's not X to the 25, right? It's actually X to the 10. I multiply those. So this is actually going to be e to the 2 normals. So, right, that's what X squared. It won't be the normal squared because it's not like we're down here. We would go X to the 5 squared. We would just multiply those. So that's what we're going to get here. X squared is just e to the 2 normals. So that's great. It's just all up in the exponent. So this is really just expected value of e to the 2 times the normal 1.5 and 9. And so here's where I'm going to use that other property. This property here where I've got something times a normal. And for me, I'm thinking about just, kind of like think about distributing it to the components, but I'll have to square it going into the second one. But that's okay, no problem. So I'm just going to sort of distribute this in here. I'll put a little square on there just for like my own little purposes. But this is expected value of e to the normal of, well, 1.5 times 2. So that's a 3. And then 2 squared, 4 times 9 is 36. And now expected value e to a normal, awesome. It's just e to the first parameter plus 1/2 the second parameter. Super easy. What is that? 3 plus 18 is 21. And again, I don't really care so much about the final answer, but I just wanted to, but the process is important, okay? Because that's what we want to do. We want to actually make the math work for us, right? Instead of just memorizing a bunch of formulas, is like, no, we want to command this stuff where to go. So just trying to help you to have that confidence to be able to do that. And what about the median of X? Oh, okay, well, the median is the 50th percentile. So we're thinking of like, oh, the percentile formula. Oh, okay, percentile formula. So I'm actually going to go back to where X was e to a normal. So we knew that. That was actually what we have in green up here. So I'm going to go back to there. But the thing is, if I wanted to know the 50th percentile of X, there's this real cool property that as long as you have kind of like nice functions here that you're working with, then you can actually just find the median of this, or the median of, yeah, the median of that distribution, and then it actually corresponds just perfect. So I want to know the median of this distribution. So to do that, I'm going to kind of go back to this formula here that we said was good for percentiles, the 50th percentile. So I'll go back to that because I'll be able to find percentiles of Z pretty easy. So I'm just going to think of this as, okay, mean plus the square root of the variance. So this is really e to the 1.5, the mean, plus square root of 9 times Z. And now I think, what was the median of Z? So the median of Z, well, Z was the standard normal distribution. That's this graph right here. The median is the 50-50 mark, right? Which for the standard normal, that would just be 0. So I could also plug it into the normal distribution calculator, and I can do n inverse of 50%. I could do that, but actually I know that it's just a 0, the median for Z. And so that gives us something really nice that just says, oh, the median of X is just X to the, well, 1.5 plus 0. Okay, so hopefully without like crazy numbers, this is going to be the kind of thing that we're going to do over and over and over again today. And when you do log normal distributions, this is going to be the exact same thing that you're going to do over and over again. It's going to be the same few things that you're going to do a ton of times. Just it's all just kind of going back to this. And it gets back to this idea about, oh, spot the normal. Once you've got the normal, then you can subtract the mean and over standard deviation. You might have to do a little bit of pre-processing to get there, a little pre-processing step, but that's okay. No problem. You could do that. Just make sure that you realize what exactly is normally distributed, right? So that's going to be my starting point for like basically all these problems today. I'm going to write out, what do I know that's normally distributed? Okay, and I'll show you how we can just apply this in so many ways. Okay, any questions about this so far?
Yeah, I got a little lost on B, how we got from the 1.5, because I don't understand.
This one here, part B? The
Yeah,
first
so
step here or the second step?
how the second step, where we got from e to the 1.5, maybe I just don't recognize,
Okay,
to the
perfect.
e to the 6.
That's this box right here. Okay, and this is going to be the one that we're going to be dealing with a ton. Expected value of e to a normal.
Okay.
And anytime we say that, we're going to say, okay, expected value of e to a normal is just going to be e to the, well, first parameter, the mean, plus 1/2 second parameter sigma squared. So yeah, well, yeah, we're going to come back to that. And that's exactly what we did on part C too. So hopefully that answers both of those. Yeah, and then that's what we did there. We're just like, oh, it's just first parameter plus 1/2 second parameter. Bam. Yeah, good. And this is going to be something, oh man, we are going to do this all day. It's just going to be such a powerful thing for us. So
yeah, I can't seem to wrap my head around if the expected value of the normal is 1.5. So why would the expected value of e to that variable be the same e to the 1.5?
yeah, it just it doesn't work that way. So just like, remember how, like if you had expected value of x squared, you can't just say, oh, that's really just expected value of x squared. I can't like kind of pull the square out. There's certain limitations to the expected value. It doesn't like sort of, you can't just sort of like pull the expected value anywhere you want within a problem. You just have to be a little bit careful. And yeah, the thing is sometimes some surprising results come up. So that's why when we officially do it, it becomes actually related to the moment generating function. To do the expected value of e to some variable is actually quite difficult. It's the moment generating function.
Got it.
Yeah. But yeah, great. Yeah, please. Yeah, thank you. Great. Any other questions so far? Because it's super important to, any little questions here, to resolve those because we're going to kind of push past this. But the cool part is that really everything we do today is going to be basically back to what we did here. Honestly, it's like it's going to almost feel a little like annoying and repetitive because we're going to like really just kind of just go back to this stuff. Okay. All right. Okay. All right, so then let's, so now here officially is the log normal distribution. Okay, so we say that X is log normally distributed if the log of X is normal, right? That's really what they mean. Okay, it seems weird. It's not like it's not X equals log of normal, right? That's how we would kind of say it in English, but that's not what we mean. We just say it's log normally distributed if the log of X is normal. Okay, and so what a lot of study materials do is these are really the important parameters, but it's not really the mean and the variance of the distribution. It's not the mean and variance of X. It's the mean and variance of log X. So a lot of times you'll see probably in your resources, they might call this M and V or M and V or V squared or something like that. I'm not sure what they'll call it, but that's probably the same sort of thing that you've seen before, but they're kind of careful not to make it sound like it's the mean and variance of the distribution of X. But I've seen, as I've like looked and worked with students and looked at their resources, it's like sometimes it's just really shady how they gotta say things. So, but we'll just, so this slide is here to maybe make a distinction between, well, what is the mean and variance of X then? Because this isn't, but sometimes they'll kind of make it sound like it is. So we'll figure that out. What is the expected value of X and the variance of X? Okay. So, but we're going to kind of do what we just did here, get another crack at it. So we know that log X is normal. So we can easily solve for X. We're just going to E both sides, right? So I'm going to have E to the normal. And if I wanted to do the expected value of X, I'm just going to plop that right in there. So this is just expected value of X. And what's X? Well, X is E to the normal of mu sigma squared. And okay, oh, now we're back to that again. Expected value of E to a normal. So go ahead and take a second and write down what you think that is. E to the what? Okay, so take a second and see what you got there. And you can flip back to the first page there, but you should have said first parameter mu plus 1/2 second parameter sigma squared. And there's not really much more we can do with this. This is as good as it gets right here. Okay, but that's it. So this is actually the mean of X. Way different from mu, isn't it? It's like not even close. So if they were to say that mu is like the mean of the distribution, they're kind of right because it's the distribution of log X, but it's not the mean of X. This is the mean of X. Totally different. What about to get the variance, then we also need expected value of X squared. So that's fine, no problem. But for us, okay, well, X squared, what does X squared equal? Well, X squared then would just be E to the 2 normal, right? That's the whole stuff with the exponents, but no problem. So this is just expected value of E to the 2 normals, mu sigma squared. All right, so before I do the whole expected value of E to a normal thing, I'm gonna distribute in that 2. So if I have to square it into the second parameter, thus this is expected value of E to the normal of 2 mu, and then 2 squared, so 4 sigma squared. And now, so take a second, write it again. What do you think this is going to be equal to? So this is expected value E to a normal. So what's this one going to be? Take a second to write it down. But if you said E to the first parameter, 2 mu, plus 1/2 second parameter, 4 sigma squared, you're totally right. Great job. And we can simplify that a smidge here. I guess E to the 2 mu plus 2 sigma squared. But it's true. Yeah, good. So what would the variance be? Well, we know what the variance is the expected value of x squared minus expected value of x squared. So I'm going to have what I put in green here, e to the 2 mu plus 2 sigma squared minus, and then, okay, expected value squared, right? So expected value of x squared minus expected value of x squared, typical variance formula. So what was the expected value of x? Well, that's what we had in blue. All right, and what does that then become? Okay, so this is going to become, well, the first one is really just e to the 2 mu plus 2 sigma squared. Let's do that again. And then what do we have here? Well, again, it's the whole exponent thing. So e to an exponent to an exponent. I'm just going to multiply that 2 in there. I'm not going to have to I'm not squaring this, right? I'm just doubling it. That's what I'm doing. So I'm going to have e to the 2 mu plus, well, just a 1 sigma squared now. And there's not really a lot I can do with this. It's just ugly. It's just plain old ugly. I guess what I could do is I could pull out e to the 2 mu out of everything. And I guess I could pull out a sigma squared, e to the sigma squared in there too. And then when I do, well, look out of that first thing, I guess I've just got an e to the sigma squared. And then I pulled everything out of the other one, so I just have a 1. So, well, so this is the variance of x. so that's the variance of x, and here's the expected value of x. So, but this is awful. The variance, expected value, I guess that's not so bad. You could memorize that, but this one is like, oh my gosh, do we need to really memorize this? Do we need to do we have to know that? And I guess my answer would be, I wouldn't memorize it, to be honest. If you want to know it, you can, but you can do sort of what we did. And when you have like exact numbers, or you can fill in more numbers in there, it won't look so awful. But I don't think it's worth memorizing, to be honest. And often they don't really ask you about the variance of stock prices or the variance of X. They really kind of tell you more about this thing. It's pretty rare for them to actually ask you to find out the variance of X. Okay. So just kind of keep that in mind. We could find the variance if we wanted, but it is a whole different animal than this thing. So just keep in mind, whenever they give you that M and the V thing, they're really talking about the mean and variance of the normal that sort of like is underneath the log normal, but it's not the mean and variance of X. Okay. The things we have circled here, those are the mean and variance of X, and they're awful. So, okay. But again, that won't come up too much. So we'll show you. All right. Okay. So when it comes to stock prices now, so now that was the log normal distribution in general, like back to P. But when they talk about log normal stock prices, okay, well, what do they mean? Well, they mean this. This should be the thing that comes to our mind first. They're like, oh, okay, well, the log of ST over S0 is normal. And sorry, that's a super tiny parentheses there. So I'm gonna make that bigger. Sorry. But this is the one that's like, oh, it's alpha minus delta minus sigma squared over 2 times T, and then sigma squared T. So that's the thing. And this is probably the thing you already have memorized. So this would be the other thing, though. If you don't have it memorized, you should get it memorized, because this will come up a ton of times. Anytime they say something like, oh, assume Black-Scholes framework, or stock S has a log normal distribution, or something like that, assume stock prices are log normally distributed. This should be the thing that comes to your mind. Okay. Now, out of all this, what's the random variable? Like, where's my X? And that's this. This is the thing that's random to me, right? The stock price in the future, like I'm here at time 0. So I don't know what the stock price is going to be in the future. So that's the thing that's random. So that's kind of like my X. And you might be looking at this and saying like, well, that doesn't look like log X to me. That looks like log of X over something to me. Is this still log normally distributed? And the answer is yes, with a quick little fix, right? We're going to always remember this, but just to sort of convince you that it really is still log normally distributed, we could actually think of this as, we could split this log up if we wanted, right? It's a log of something over something. So we could say log of ST minus log of S0. We could write that, right? And if we did, we'd say that, oh, log of ST was equal to, and then I could just kind of move this over. So it'll be log of S0 plus that normal distribution, alpha minus delta minus sigma squared over 2 T sigma squared T. And what happens now if I add a constant to a normal distribution? Well, it'll add into the mean, but it won't affect the variance, right? So we could actually say that this is really normal of, well, log of S0 plus alpha minus delta minus sigma squared over 2T, and then sigma squared T. Now that actually won't relate to what I want to talk about in this slide, but this actually gets at something that's real important for us to know, or to recognize at least. Okay, up to here, is this okay? I don't want to go like too fast through it, but hopefully you've seen this. That's probably comfortable to you, especially if you've been doing this for a while. So that's fine. We could, if we wanted, we don't usually do this, but if we wanted, we could actually legitimately solve for log of ST. So we could solve for that if we wanted, and that we just kind of split it up and then move the log of S0. It's just a constant, right? Log of current stock price. So if it's like 100 or whatever, it's just log of 100. But it's just a constant I'm adding. So I can absorb it into the first parameter, but it won't really affect the second parameter. Okay. Now, the reason I bring that up is because you'll see in a lot of problems, they will say something like, oh, what is the variance of the log of ST? Or something like that. Or maybe they'll say something like, oh, they'll give you the list of things they know, and they'll say, oh, they'll know this is, 0.09 T or something like that. So it looks really awful. It looks like, oh my gosh, the log of ST, and it's like variance of a log. Oh my gosh, I'm so scared right now. But honestly, they're just saying the variance of this. But the variance of that is exactly the same as the variance of the original log of ST over S0, right? Because that log of S0 won't affect the variance at all. So really all they're doing is they're telling you, oh, this is sigma squared T. It's nothing more than that. That's all it is. And they can make it even scarier. They could say something like, oh, variance of the log of ST given S0 is 100 or something like that. But then you're like, well, I don't care. I don't care what S0 is. That doesn't affect the variance. It's still, sigma squared T. Right? It's still that. They could even like not put the 100, but they might just say log of ST given S0. And you're like, oh man, that looks kind of scary. But actually, it's still the same thing, because that log of S0 won't really affect it. What might affect it is if they actually said S1. So if they said actually, and I'm digressing here a little bit here, but if they were actually to say the variance of log of S4 given S1 is 0.27. Well, actually, now that is significant, because this given S1, that means like, oh, if you know S1, basically if you're starting at S1, what's the variance at time 4? That's really 3 years worth of growth. So that just means that sigma squared times 3 is 0.27. Right? I haven't seen that too much, but I feel like they could easily write something like that. So totally fine. But yeah, there you go. And then you can solve for sigma squared there. Right? But it looks really intimidating and awful, but it's really not that bad. Okay. Now, if they were to say something like variance of ST equals something, that would be awful. Okay, and I'll show you that in a minute, but that would be a very horrible, like this would be worse for us than if they said variance of log of ST. Okay, and then they might say something about like the variance of the log of the forward price or something. It's the same thing. It's the same variance and stuff. So So you kind of hope that they have a log in there, because then if they talk about the log of the stock, now they're talking about the normal distribution, because the log of X is normal, right? That's what they're dealing. That's what they mean by that. Okay. Now, so just to show you basically how you would find that, right? So let's go back to this now. So now kind of what I have on these slides, sorry, I digressed, but I just kind of felt it going there. So they talk about S0. Well, okay, back to this original thing here. If I know log of ST over S0 is normal. Well, if I wanted to solve for ST, that's fine. I would just, in this case, I would E both sides. That would get rid of this. But then I'd also have this extra step that I'd have to multiply both sides by S0. So this one's going to be S0 E to the normal. Right, and it's just kind of a lot of writing. Alpha minus delta minus sigma squared over 2t, sigma squared t. But all that's up in the exponent. But that's it. ST is just S0 E to the normal. Right, kind of like what we did before with the X. You know, just go there. And so if I wanted to know the expected stock price, expected ST, that's just going to be expected this thing. So expected S0 E to the normal. Okay, and now we can think of, well, we can think of back to what we did before with that one thing in the red box. So expected value of B to a normal. So because this S0, it's a constant as far as the expected value is concerned, it can just come out. So this is S0. And then what's left is that I'm going to have expected value E to a normal. So what do you think that would be? E to the what? Go ahead and say it in your mind. Expected value E to a normal is E to the first parameter, alpha minus delta minus sigma squared over 2t plus 1/2 second parameter, 1/2 sigma squared t. Super easy. And oh, that's actually kind of nice because it simplifies it out a little bit, right? Because I've got a minus 1/2 sigma squared t and a plus 1/2 sigma squared t. Oh, that's kind of cool. Those are going to cancel. And all I'm going to be left with is alpha minus delta times t. And honestly, you might even have this formula already memorized. This is expected value of the stock price. And if you don't have it memorized, it's kind of a good one to have. You don't actually need it. We could do it this way each time, but it comes up enough where it's kind of better if you have it already memorized. Okay, and we're going to come back to this formula a little bit later anyway, but we'll use this. So if it's just the expected stock price in a year, it's just, oh, current price and then E to the alpha minus delta t. And we talked about that, I think it's the first seminar, but the whole alpha is the expected return. It takes into account how much the stock itself is going to grow, as well as extra dividends. But this is asking me just about stock price only. So that's why we take the full expected return, but kind of eliminate the effect from the dividends. And that just gives us stuff about stock price. So it's kind of neat that way. And they call this the rate of appreciation, because that is how much the stock itself actually goes up, how much the stock raises in value, how much it appreciates. So they call that the rate of appreciation. Okay. Now, if I wanted to find variance, so if they ask me for the variance of ST, so here's expected value of ST, well, what would I need to find? I would also need to find expected value of ST squared, which is doable. I would just square this thing first. And it's ugly. I'd have S0 squared and then E to the 2 normals. And then that 2 I would have to, distribute in, and then the square into the second one. And I can do that all out, and then I just end up with E to the, expected value E to a normal plus something. And then from there, then we would just do the whole expected value E to a normal is E to the first parameter plus 1/2 seconds. We could do that. And then once we get that, we'd have to subtract this squared to get the it's kind of a big process for that. So But that's what we would actually have to do if we wanted to find the variance. We would have to do that whole thing, and it's just not simple looking. It's ugly. But if you needed to do it, you could do it. That would actually be a very hard part of a problem, but it's probably not something that has an easy formula for us to remember. And it might be on their formula sheet because they just kind of want to just have you just memorize a bunch of formulas. But I don't think that's good. And I think it's better for you to come up with it on the fly if you need it. It's not that hard to do, especially if they give you actual numbers. It's sort of like harder with all the letters. But if you just if they gave you all the numbers, you can just kind of put it in, and actually it'd be a pretty quick thing to do. Probably easier than using the formula in a way, which is super weird. Oh, and then we had a question here too. So I don't know how long it's been up there, but someone asked, could we change S0 to S1 if we know the value at S1? Yes. So yeah, we'll come up to that in the next problem. But yeah, this S0, it doesn't always have to be an S0. It usually is because that's kind of where we are. But they could give you like, oh, what if you actually knew S1? And then you could do this for S1, but then the time would just have to reflect the amount of time elapsed. Okay, so that's kind of the big thing, is the time here is just the time elapsed. So if you're going from time 2 to t or whatever, then this would actually be like a t minus 2, whatever that is, you know. But that's it, actually real easy. It's real nice. It's real flexible that way. So that's good. All right, well, let's put some of this into practice here as we look at the next slide. So let's kind of put all this together here, and I'll show you how I kind of start these problems, and you'll see that probably today I'm going to kind of start them all the same way. Just do it kind of every question all about the same way. So, but I'll show you some kind of techniques along the way too that can help you solve harder problems. So, okay, what do we have here? So stock has a current price of 100. So that's what S0 is 100. It pays continuous dividends. Delta is 0.04. Expected return alpha is 0.15, volatility 0.2. So honestly, these problems are a little bit boring that way, right? Because they just have to list so much stuff. So sometimes they'll do it in bullet points. They'll try to be creative about how they say stuff, but it's really, they're just presenting all the information to you. That's all they're doing. Determine the following. Okay, the probability that the price in 2 years is going to be between a 105 and a 110. All right. So, well, since I know that I'm dealing with log normal stock prices, I'm going to say here that the log of ST over S0 is normally distributed with the alpha minus delta minus sigma squared over 2 times t and sigma squared t. So I'm just going to kind of like, before the problem even starts, I'm going to actually just kind of put that in 0.15 minus 0.04 minus 0.2 squared over 2. And then I'm going to leave the t open because sometimes they're asking me 2 years, sometimes 5 years, sometimes 4 years. So I'm just going to kind of leave it in general for now. I'll just kind of leave it as a general t. And then we've got sigma squared 0.2 squared times t. So let me see what this all comes out to. 0.15 minus 0.04 minus 0.2 squared over 2. And I got 0.09 t for the first parameter, and then 0.04 t for the second. Okay. So, all right, and it does depend on time, how much time will be elapsed, but this will kind of be my starting point for every single problem. If they tell you the time, then you can put that in right away. But for this one, I just kind of want to give different times just to show you. But at any rate, okay, probability that the price in 2 years will be between 105 and 110. So here's what I'm going to write. Probability that the price is between, so S2 basically is between 105 and 110. That's the question. What's the price that the stock, what's the probability the stock price in 2 years will be between a 105 and 110? Simply, that's it. So for me, I realize that I'm going to need S2. So I'm going to kind of come here and I'm just going to apply this with t equals 2 because I just know stuff about time 0. So log of S2 over S0 is normal with, well, t equals 2. So what's that going to be? 0.18 and 0.08. That's it. Okay, so that's okay, right? So far, so 0.18 and 0.08. So now what do I do? Well, I have to realize that what's normally distributed here? Well, it's not S2. S2 is not normally distributed, but this monster, that monster is just normally distributed. So I'm going to have to do a little bit more pre-processing here. I'm going to have to divide by S0 and do the natural log. But that's okay. It's not bad. So S0, I actually know what S0 is, 100. So you could put them all as S0s or all as 100s, or maybe the middle one is S0, the outside is whatever, it doesn't matter. And then the other thing is the natural log. So I'm going to have to do the log of everything too. So that's my pre-processing step. It's actually 2 steps, but that's okay. Divide by S0, take the log, all that's fine. And so then this actually becomes, okay, well, I'm just going to get something. I'm going to be able to standardize, and the log of S2 over S0, that was normal. So that's the thing that's going to become standard normal. So that's going to become a Z. And I just need to, yeah, kind of find out what those other 2 things were. So I'm actually have a log of 105 over 100 minus the mean. And actually the mean is real innocent looking now. It's just the 0.18. So minus 0.18 over the standard deviation square root 0.08. And it's just going to be a number. That's all it is. But I could do the same thing to the other side. Well, it was this, but I standardize, which means I subtract the mean over standard deviation. So log of 110 over 100 minus the mean 0.18 over standard deviation 0.08. And let's kind of write out what that is here. So let's compute out those values. Log of 105 over 100 minus 0.18, and then over square root 0.08. I got negative 0.463896, whatever. I think you have to use 5 decimal places if you use the calculator, right? So what would that be? 390. And then, okay, how about I do the other one? Log of 110 over 100 minus 0.18 over square root 0.08. So again, that's the normal distribution, just doing that, minus 0.29942. And now we think of like, okay, how did I do this with the probability of being between 2 values, especially if it was back in like probability exam. If you had capital F, well, you would do F of the big minus F of the small. And for us, that's the capital N. So I'm actually just going to do straight up N of the big one. So N of negative 0.29942 minus N of the small one, negative 46390. And I'm just going to plug both those in. Notice how I didn't like negate it. It's not like I'm doing probability Z greater than here. So I'm not going to like negate that one or anything. That's not what I'm doing. I'm just doing like back if I had like back in exam P, if I had something like that, if I used capital F, it would just be F of B minus F of A. It's just that thing. That's all I'm doing. But instead of F, I'm using capital N. And instead of X, I've got Z. That's all I'm doing here. Okay. But at any rate, so then you can look up those values just for the sake of time. This ultimately ends up with 0.06095. So feel free to kind of look up those specifics later. So we'll keep going. But
So for this one in the calculator, I just used a normal one, not the inverse, and I put in negative
good.
0.29 in there.
Good. The negative there and the negative there. Good. And I didn't actually write down what each of those were individually, but my final answer was 06095. So sorry, I don't actually have what those were. But yeah, you type those in just as a regular as X because you want N of X. Good. Yeah. Excellent. Yeah, great question. Good. All right, B. what about expected value of the square root of the stock price in 5 years? Okay, well, all right, what are they talking about? Stock price in 5 years. So I need to know something about S5 over S0. Okay, well, actually, for me, that's great. I already have it in terms of T, so I can actually just plug in T equals 5 in there. So this is N of, and then would that be 45 and 20? I plugged in T equals 0. So I'm going to do this here with T, sorry, T equals 5. So I'm just going to plug in T equals 5 there. All right, and then I can think of, all right, how am I going to use this now? But that's my starting point. I'm really asking something about S5, but they want to know the expected value of the square root of S5. Or as far as exponents go, this is expected value of S5 to the half. So as long as I can find an expression for S5, I'm good. But I can actually, kind of solve for that out here. So S5 is, so I'd have to undo the logs. I'll e both sides and I'll multiply by S0. So I've got S0 e to the normal of 0.45 and 0.20. All right, so just kind of twisting that around, solving for S5. That's all we're doing. And great, I'm just gonna, plug that in, and S0 is 100, so I'll just probably plug that into right away. But this is gonna be expected value of, well, 100 e to the normal. And all of that's gonna be square rooted. So what would that mean as far as the exponent of a half? I guess the 100 would be to the 1/2 or the square root, however you want to look at it. It's kind of easy to take the square root, so it's nice to see it as that, but it's okay. And then what about the 1/2 here? What would I do there? Well, it's really, that's all raised to the 1/2, but I'm just going to really multiply it into the exponent. So this is just going to be 1/2 times the normal. And then I'm just going to do what I did before. I'm going to, distribute it in there and square into the second thing. And so this is expected value of 10 e to the normal of, and then, yeah, the 0.45 over 2. So I think that's what, 22.5. So 0.225, because I'm multiplying the half into the first, and then I'm multiplying the second one in as a quarter, which I think gives me 0.05. Right, 20 divided by 4, so 0.05. But again, do all this stuff in your calculator. Don't really trust yourself mentally with math, like just do it like that. And great, it's an expected value. I can pull the 10 out. This is really 10 times, well, expected value e to a normal. Now we're coming back to that again, right? Expected value e to a normal is e to the first parameter plus 1/2 second parameter. Easy peasy. And yeah, whatever that comes out to be, 10 e to the 0.25. So yeah, whatever that evaluates to, but yeah, that's it. Okay. Does that look like a 0.05? Sorry, it should look at 0.25. Sorry, let me know if you have a hard time reading some numbers or whatever. I don't know what the resolution looks like for you. Hopefully it's big enough, but I don't know what Zoom's resolution is. So just let me know if you need me to kind of be a little bit more big or larger or something like that, if that's the case. All right, now what about C, the 95th percentile? Okay, percentile, we kind of know what to think of. That whole, a normal could be the mean plus square root of the variance times z. So I'm kind of thinking that, because they're asking about percentiles. Okay, so what to do. So the 95th percentile of stock price in 4 years, given that the price in 1 year is a 110. Okay, well now we actually want to use the distribution. So I'd really want to know the log of S4 given S1. But that's cool, because that's just going to be, well, here, I guess I'm going to go back to this again, because it's the same thing. Instead of starting at 0, I'm starting at 1. But again, it's all about how many years growth there was there. So this is all about 3 years worth of growth. So now I'm going to use here that T is 3. So I'm going to get what? 27 and 12. 0.27 and 0.12. And so they want to know the 95th percentile of the stock price of S4. So I'm going to solve this for S4 again. S4 is, and then kind of a real familiar thing for us, right? I have to eat both sides, multiply by S1. So I get S1 e to the normal. But since I'm talking about percentiles, now I kind of want to change this normal to that whole like mean plus square root of the variance times z, because I'd really like to know something about z. In fact, I'm going to need to know the 95th percentile of z. So this is actually S1 e to the mean 0.27 plus square root of 0.12 times z. And that goes all the way back to that first page, just right above that red box, that thing we did with about percentiles. So here's how I'm going to finish this one off, right? So if I want to know the 95th percentile of S4, I just need to know the 95th percentile of Z and just kind of plug it all in. So how do I find the 95th percentile of Z? What is that going to be? Well, that's just going to be an inverse of 0.95. Super easy, because I want to know, basically, I'm on this graph here, and I want to know, oh, what point here, what Z value is going to give me 95% here. So normally we have the Z and we want the probability, but here we're going to have to go the other way around. So I know the probability, I want the Z, so I'm going to have to do an inverse. And when I did that, I got 1.64485. So then if I want the 95th percentile of S4, that's going to be S1, and we know S1 is 110, so 110 e to the 0.27 plus square root of 0.12 times the Z value, 1.64485. So it seems a little bit surprising maybe that you can do this, where you're like, wait, if I want the 95th percentile of S, I could just find the 95th percentile of Z. But yeah, it's actually a super cool property about these. And it's because the E is increasing and all this stuff is increasing. So it's actually like nice continuous increasing functions. That's kind of, I think that's what you need for that. But let's compute it all out. 110 e to the 0.27 plus square root 0.12 times 1.64485. And I got here 254.75-ish. Okay. Any questions about what we have on this page? Hopefully it's coming more clear. I'm trying to just basically do the same few things over and over and over again, because that's really what I want you. I just want you to get good at using what you know, instead of like having to come up with all these formulas and stuff, because I think they probably actually have formulas for all these things. But it actually all goes back to the same basic few things that we're going to do. First, find the distribution of the thing that you're after, and then apply that to the problem they ask. Okay. Now, the next part, it's actually kind of a continuation of this one, but the next one is one where we're going to actually have to know a specific technique. We can't really do this without this technique. So I just wanted to show you that one here. So this one here is the covariance of the year 5, the year 3 and the year 5 prices. So I'm really after covariance of S3 and S5. Okay. And just to kind of put what we had on the other side, I had log ST over S0 was N of 0.09T and 0.04T, right? Just what we had before, because we're going to need that same thing. All right, now here's the problem, right? We might think like, well, are these things, is the covariance even positive? Like, is there a covariance or not? And well, I guess if the answer was 0, that would be a super That's a lot of wasted paper. So that's probably not the case. In fact, this is a very hard problem if you haven't seen this technique. Actually, I don't think you can do it if you don't know the technique. Because what they're really asking for is, you're like, okay, here's the current stock price, and I know, like, you know, it's going to kind of wiggle up and down, and you know, it's who knows what it's going to do. Feel free to draw whatever picture you want, but like, you know, stock prices, they're always up and down. And they're saying, I want the stock 3 price, or the time 3 price, and the time 5 price. So the time 3 price, I don't know, might be there on my picture. So that's S3. And then the time 5 price is up here. So that's like S5. So they would really like to know the covariance between these two prices. Now they are connected though. One, S5 definitely depends on S3. Because if S3 was like super low for some reason, then having this same price would be like extra hard, you know? So it depends on, so S5 is definitely going to depend on S3. So they're not independent. So this covariance, I got to figure out how to do it. Okay. Now, back to covariance, the way that we did it back in exam P is we just did the expected value of the product, S3, S5, minus the expected value of each thing separate. So this is going to be our starting point, S3 times S5. Okay, now these two are actually going to be real easy. I could, if I want, I could go back to this formula and put in S3 and S5. But actually, I think what we'll do is we'll sort of go back to that quicker formula a few pages ago, where the expected value of S is just S0e to the alpha minus delta times T. Remember that one? So this one down here. So this one, the expected value at time T is just S0 e to the alpha minus delta T. So that's always kind of a good one to know. Here's a place where that might actually come in really handy. So S3 would be S0, 100, e to the, well, alpha minus delta. What were alpha and delta? So 0.15 and 0.04. So if I did alpha minus delta, that's what, 11, 0.11. So I'm just going to have that times 3. So this will be 0.33. Right, alpha minus delta T. And then the other one here is just going to be kind of the same thing, 100 e to the alpha minus delta. Well, that's 0.11 times 5. So this is 0.55. So those are actually really easy. So here we used expected value of ST is S0 e to the alpha minus delta T. Sorry, it's a little cramped there. Apologize. Move that over. Okay, so I kind of use that there. That just kind of gets those done quicker, but now is the hard part. Now's this one. Okay, how do I do this? This is always the toughie. Okay, now it would be super nice if I could just kind of split these up. I could say, oh man, that would just be expected value of S3 times expected value of S5, but I can't do that because they're not independent. And if I did, by the way, wouldn't that just be this? And the answer would be 0. So you're like, okay, I feel like I can't do that. Maybe I'm not really sure why, but it's because they're not independent. If they're independent, yeah, I can split products, no problem. So I have to find a workaround. How do I do expected value of S3 times S5? That's the big question. So here's the technique that you'll need to know about. And this could come up with a variance of S3 plus S5. And this could come up with in a question like that, because there you have to know that S3 and S5 are not independent. So I'm going to have a covariance term, and I'm going to have basically the same kind of thing here. Or they could actually ask you something about the product of stock prices, like for a geometric average Asian option. Those you have to deal with the product of stock prices. So that comes up a lot. And in fact, those are actually doable, but the arithmetic average ones are actually really hard. So, but whatever. So, okay, how do I do this? How do I actually get this? Well, I do need to split it apart. Here's the technique. Or here, well, here's the observation, and we're going to see how to exploit it. So the observation is that it's true that S3 is connected to S5. And if I just wanted to know the time 3 price and time 5 price, yeah, they're connected. So it's really hard to tell one like separate from the other. However, the cool part is that if I sort of thought about this part compared to this part, now those two parts are independent, right? I mean, S5 is really like if I had the red curve drawn all the way from the beginning, that would be like S5, but I'm not doing that exactly. I'm actually kind of separating like what happens in the first 3 years and then what happens in the last 2. Okay, now log normal distribution of stock prices have this beautiful property that if I'm on non-overlapping intervals, then those actually are independent. Okay, and if you think about it, that makes sense. All it's really talking about is basically like, what's my growth? How much growth am I doing here? And even back to like these expressions with S, you think about the normal distribution here, it really is like expected value, like SE to the exponent. And in the exponent there, that's where we talk about sort of like the growth of this thing. And that's really all these normal distributions are, is they're talking about the growth over these different intervals. So the growth from 0 to 3 is completely separate from the growth from 3 to 5. Right? Those growths, it's just like 3 years worth of growth, and then kind of, it doesn't really matter where I'm at, it'll just grow 2 years worth of growth from there. So we're going to exploit that independence, and we're going to say, let's do quotient number 1 is just going to be the time 3 price over time 0. And quotient 2, we'll talk about sort of the growth over the last interval, S5 over S3. Now these two Q's, they're quotients of prices end over beginning. It's just really, these are just kind of growths over those intervals. These two are independent. And so, and the cool part then is that I can rewrite this as the Q's, as the Q's, in terms of the Q's. So this is going to be expected value of, well, what is S3 in terms of the Q's? I guess for that, I'd use the green one. So the green one is S0 times Q1. And then what about Q2? Well, S5, I guess that's the other one here, S5. Well, S5 is S3 times Q2. So I'm just going to kind of write that here, S3 Q2. But S3 is actually what I had in the green. So this is going to be S0 Q1 Q2. And look for this sort of like chain of things here, right? And it kind of makes sense anyway if you talk about growth, because it's like, oh yeah, the growth to time 5 would be, well, the growth from 0 to 3 and then the growth from 3 to 5 stacked on top of it. So it kind of makes sense anyway. But just sort of mathematically, that's what's happening here. Oh, and maybe I can actually put this in green just to help you see a little bit easier too. So S5 is Q2 times S3. S3 itself was Q1 times S0. But the nice thing here is that, all right, now I can actually get this in terms of the Q's. So this is expected value of, I guess I'm going to have S0 squared, Q1 squared, and Q2. And now because the Q's are independent, now I can split those out. So S0 squared, that's just 100 squared. I'm just going to pull that out of the expected value altogether, 100 squared. And then now I've got expected value of Q1 squared times expected value of Q2. Beautiful. Oh, we love this, because now, because they're independent, the Q's are independent, I can split that product up. And that's kind of the whole trick that we got to do, is we need some independence somehow to get that. All right, well now let's, how can we get these expected values? But we're going to see that it's actually back to the same things that we did before. So what do I know about Q1? And I know, what do I know about Q1? Well, first of all, I know that it's S3 over S0. For me though, I would actually, that kind of looks familiar, S3 over S0, but instead I would actually prefer to see log of S3 over S0. So what I'm going to do is I think I'll just kind of maybe put the log on both sides. Because I mean, that's certainly true too. If Q1 is S3 over S0, then the log of Q1 is the log of S3 over S0. So no problem there. And then now, because it's the log of S3 over S0, that's really just this whole normal distribution here with T equals 3, right? So this is just going to be N of, well, what T equals 3 is 0.27 and 0.12. And I'm going to do the same thing with Q2. So let's see if we can kind of figure out what that one is. Well, what do I know about Q2? Q2 is S5 over S3. Really, for me, because of these log normal distributions, I actually prefer log of that. That's kind of the better thing for me to see. And then this is going to be a normal distribution. What do you think the T I'm going to use here is? If you said 2, great job. That's exactly right, 2, because I'm really just talking about 2 years worth of growth here. So this is going to be with T equals 2, so that's going to be an 18 and an 8. 18 and 0.08. All right, now what do I do with these? Okay, because that still doesn't actually answer this for me, but it's actually really close, right? We're actually right there. I need to know what is Q1 squared. So I'm going to come back to here and I'll be like, well, I want Q1 squared. So first of all, what's Q1? Q1 would be, well, I guess I just have to get rid of the logs. I'd have to e both sides. So Q1 is just e to the normal. So what would Q1 squared be? Well, I guess it's just, that'd be that e to the normal squared, but it'd just be e to the 2 normal. So that's going to be really nice. This is 100 squared expected value of, okay, Q1 squared. What's Q1 squared? E to the 2 normals of 0.27 and 0.12. Right? I'm just taking this, squaring it, which just means 2 there, and that's it. And then what about expected value of Q2? Well, what do I know about Q2? Well, here's, this one's actually easier, right? Q2, if I wanted to solve for Q2, I'd have to e both sides. So I'm going to get e to the normal 0.18, 0.08. And then I'm just going to get here that this is expected value of e to the normal, because that's what Q2 is, e to the normal of 0.18, 0.08. And now you don't have to really worry so much about like, wait, should I have like an S0 or should I like, wait, what's going on? Why don't I have an S0 here? But we're just kind of letting the math work for us, right? We're kind of just following where it takes us. We're not trying to use formulas, right? We're trying not to be formula driven. We're trying to be like, oh, let me just understand what I'm doing so that I can make it work for me. Okay, and that's exactly what we're doing here. And so then I have to go back to these basic principles and, oh, okay. And then question 2 for Q2, could we do the e to the alpha minus delta thing? Yeah, you could. It's a little harder to see here, but you could. I would be, so could you use kind of like this formula? That's the question. And you could, but you'd have to be a little bit careful because, well, there is no like stock. I feel like it would be easy to get confused with like, oh, do you do like S3 times e to the whatever or what? But it actually turns out that like the S0 would be 1 in that case. So it might be a little confusing if you tried to apply that, but you could if you were creative. Distribute that 2 in, it's going to square into there. So I'm going to have, it's just like now it's just kind of routine stuff, right? We've done this a few times. And then, okay, well, I'm going to have expected value of e to the normal with now 2 times 27. So what's that? 54. And then 2 squared, 4 times 12 is 48. And then this one, expected value e to a normal, I can just kind of do that one right now. So that's going to be e to the first parameter plus 1/2 second parameter. And then this one, okay, so 100 squared expected. So expected value e to a normal is again e to the first parameter plus 1/2 second parameter. Then this one is, well, honestly, you can just keep it like that if you want, or you can work it all out. What is it going to be? 22. And by the way, that would actually be 2 years worth of growth at 11%. That same one there. So you could, but notice how you don't have the S0 there. So as long as you can kind of keep that straight. But yeah, good. Kind of just, yeah, just work this all out and it becomes 100 squared e to the, and okay, when I did this before, I just kind of add all this out. It actually becomes e to the 1. So that's a little surprising, but okay, it is what it is. That's fine. So e to the 1. So actually that's nice because then all of this is actually the missing piece here, 100 squared e to the 1, and then minus these two things over here. And that's just going to give me my final answer. And I got 3,073.82 when I multiplied all that out. But honestly, that's not the hard part. The technique here is the thing that we were interested in. Okay. The covariance kind of works logically. It was basically the same thing that we've done back in exam P. So that was good. But yeah, the way we had to carry this one out, these covariance ones are a monster. And I've seen sometimes they have these like formulas that you could do for it, but honestly, I'm like, if you do a couple for practice, it becomes really natural. It's actually not super hard. It just feels like there's like all this information thrown at you. But it kind of goes back to this whole basic principle, like, okay, these two growths are independent. That's the thing to exploit. Okay. And then as long as you can keep track of what you're doing and try not to go to like formulas or whatever, you can totally solve those, just remembering to go back to kind of the basics, which is the beautiful part. Okay. All right, now I just want to do one more problem here before we just take a little 5-minute kind of while we're on this sort of train of thought here. You've probably seen a bunch of questions like this, and I'm sure that you kind of have a good technique for doing it. I just wanted to show you how this applies to what we're doing here to kind of help you to maybe see how this relates. So, okay, so what do they have here? Well, here they've got monthly prices for a stock for the end of each month for 4 months. And then assuming the stock price is log normally distributed, all right, estimate the expected annual return and annual volatility of the stock if there's dividends at 2%. Okay, all right, so let's see what we can do here. All right, so for me, the way that I see this is we're really asking about 1 month's worth of growth. So basically that's like S of 1 month compared to S0, or S of month 2 price compared to S1 price, or what? It's just 1 month's worth of growth. That's the thing. And this is normally distributed with alpha minus delta, which is 0.02, minus sigma squared over 2 times t. And what do you think the t is going to be here? It's a month's worth of growth. So that's a 1/12. And then I've got sigma squared times the 12th. And I'm really looking for the alpha and the sigma. That's really what they're after. They want the annual return and annual volatility. Right, those are the two things that they're after here. But I'm going to think about this like this is really the thing that I'm after here. So what I would love to have is I would love to have sample points, not of the stock prices, but I'd really like sample points that look like this, because those sample points should be normally distributed, right? Those are normally distributed. I know the mean that they should have and the variance that they should have. But if I had sample points of this shape, oh man, that would be so much better. So that's why you do that. The first step here is you would do, okay, log of the end over the beginning, right? 62 over 60. here you do log of 63 over 62, because this is really like the log of S 1 month over S0, right? The log of the next months over the previous months. Because this is going to give us now 4 sample points. 64 over 61. This now gives us 4 sample points that all sort of like fit this normal distribution over here. And we kind of remember from like stats class, even back from like maybe early college or something, right? If I've got a sample, this sample of 4 values here, if I have a sample, if I took the average of those samples, that would be a good estimator for the average of the distribution. And if I did the standard deviation of these sample, the sample standard deviation, that would give me a good estimation for the standard deviation of the distribution. Right? And that's all we're going to do. We're just saying like, oh, okay, I just need to know the mean and the variance of those things. And you could do it by hand, but you know, that's where we use the calculator. We just kind of plug these values into table 1 and have it compute the mean and standard deviation for us. That's all we're doing. So we'll just kind of do that in here. So we'll do log of 62 over 60, log of 63 over 62, log of 61 over 63, and log of 64 over 61. And then I'll go quit and then do my stats, my 1 variable stats. Okay. And then what I found when I entered these into the calculator, oh, I'm sure you guys have done that already, right? But anybody not done that? Do you need help going into the calculator? I feel like probably it's a pretty common thing. You probably already encountered it. But yeah, just enter these values into the calculator because we do need to kind of compute out their mean and standard deviation. That's it. And then when I'm on my printout here, I've got that the X bar is 0.01613 ... And then we want the standard deviation for the sample. So SX is 0.0348, that number. Okay. So this is you have to do the sample standard deviation instead of population because this is just 4 values from the whole, it's just a sample from that normal distribution. It's not the whole distribution. So that's why we do a sample standard deviation there. Okay, now what's the point? Because, well, just like what we said, this should be approximately equal to the mean of the distribution. So this is approximately equal to alpha minus 0.02 minus sigma squared over 2 times the 12th. And then this is approximately equal to the, well, not the variance, but standard deviation. So sigma square roots of 1/12, right? Just the square root of this thing. But these are estimates for those things. That's all it is. And so I guess the easier place for me to start would be the second equation there. So the cool part is that you don't have to rewrite those numbers. You can actually scroll down to the SX and type enter, and then it puts that out on the screen. That's cool. And then I guess for me, I'd multiply it by square root of 12. So times square root of 12. And that gives me that sigma is 0.12059, whatever. I'm going to store that in for X, but that's one of my answers. That's the annual volatility. So maybe that's even far enough. Maybe that'll narrow your choices down and you can just get that. But actually, it's not too hard because now what I'm going to do is I'm going to kind of put that number, that is actually the sigma up here. So I can now solve this equation for alpha. So that's nice. So I'm going to have to go back to retrieve the 0.01613. And again, it's probably easier instead of retyping it, but you could just go second and stat. And now you might see that there's a third option down there, stat vars, stat variables, right? So that just kind of gives you that screen again, the stat variables. And now just scroll down to X bar. So I got X bar, and so that's that 0.0163. So first thing for me, I'm going to multiply by 12. Then I'm going to add the 0.02 and then add sigma squared over 2. So yes, let's find out alpha. So times 12 plus 0.02 and then plus that sigma squared, so x squared over 2. And for there, I got 22088 dot, dot, dot. And that's what I got for alpha. But I just wanted to show you this because we've seen, like, I don't know, maybe you've done these problems and they're like, oh, just multiply by square root of 12 or divide by square root of 12 or whatever. And you're like, okay, how do I know to multiply or divide? And I don't know if you've ever got, or like, why is it a 12 and not a square root of 12, or, you know, kind of things like that. And so this is actually the reason. This is the reason behind it all. It's perfectly logical what they're doing, but just instead of you kind of just memorizing some process, here you kind of know exactly what you're doing. So that's great. Good. And then just had a question about, is the SX, is that standard deviation or variance? And so great question. And the only thing different would be if it was S squared, that would be like the sample variance. But here it's just, yeah, so good. All right, well, let's take a couple minutes and then we'll come back and then we'll get into the last part of our seminar today about these expected values, probabilities, D1s, D2s, Black-Scholes, and yeah, it's great. Okay, all right, so let's come on back in a couple minutes. All right, welcome back. Okay, now during the break, someone asked a question here about how do we know when we can do log normal distributions? Because sometimes they might not say the words log normal, but actually if they say like, oh, assume a Black-Scholes framework too, that's log normally distributed. So you can assume that from there. Okay, and I think that was kind of what you were saying too. Came across a question, just said assume Black-Scholes. But yeah, Black-Scholes assumes that stocks are log normally distributed. In fact, probably on almost every question, like they might not even say it, but they're always assuming that stocks are log normally distributed. Okay, so now, okay, so what we're gonna do here now is that we're gonna kind of like build off of all the things that we just did. Now, all we did is you saw we kind of just did the same few things over and over and over. It kind of always went back to the same distribution. But now we're going to give you a few more tools to expand what you're able to do. So we just want to make a few more connections here. And then this is just going to, man, you're going to be able to do so many, solve so many problems. It's going to be great. So first of all, one thing is that they might ask you for, so what is the probability that S is greater than K? So this is a big one, right? This is that stock is more than the strike. And again, they kind of start with the same thing, log of ST over S0. In fact, it's kind of boring writing this, right? Normal alpha minus delta minus sigma squared over 2t, sigma squared t. And okay, well, I guess we know what to do, right? We're gonna divide by S0, take the log, right? Because we need to first pre-process to get the thing that's normally distributed. And then we're gonna subtract the mean over standard deviation. So this is gonna become probability of, well, here's the random variable, that's the normal thing. So we're gonna subtract the mean over standard deviation. That's gonna become Z. And then the other one, I'm just gonna have to, okay, log of K over S0 minus the mean. And what was the mean? Okay, oh, that's that big alpha minus delta minus sigma squared over 2t. Then over standard deviation, and what is that? Sigma square roots of t. All right, and now we get back to like, okay, probability Z greater than, oh wait, what do we do for probability Z? Oh, probability Z less than was just N of, but greater than was N of negative. So this is just N of negative all that stuff. That's all it is. So N of negative all that. I'll write it here. You could probably just save time and not write it if you don't want, but I'll put it here just for completeness. Log of K over S0 minus alpha minus delta minus sigma squared over 2t, sigma square roots of t. Okay, no problem. And then what do we do from here? Well, just kind of, they like to just distribute the minus in there. So if I distributed the minus to the log, right, the log, it would actually become an exponent. So it would be the K over S0 inverse. So that would just kind of flip it. So it's just going to be log of S0 over K. And then I'll distribute to this minus, making it a plus alpha minus delta minus sigma squared over 2t, all over sigma square roots of t. Now, this is actually what they call d2 hat. It's exactly d2 hat. That's all it is. Log of S over K, alpha minus delta minus sigma squared over 2t over sigma square roots of t. That minus is the only thing different from the d1. d1 is just plus the sigma squared over 2 instead of minus. But yeah, it turns out that for probabilities, anytime you're dealing with a probability, it's going to have something to do with d2, not d1. So it might feel a little surprising, but that's okay. They just call this d2 hat. Now, I don't really use d2 hat, especially if it's a probability. If they said, oh, what's the probability the stock is more than the strike? I would actually probably just go through the process. You'd probably have all the numbers though, so it wouldn't look as complicated and you can get it quicker. I probably wouldn't find D2 and then just do N of D2 or D2 hat and find that. I probably wouldn't do that. I probably would just go through the process because it's easy enough. But what if I wanted the complement? What if I wanted the stock price less than K? Well, it would just be the complement of this. It doesn't make it D1, but it just is N of negative D2 hat. Right, that's the complement. Instead of being greater, it's less than, but that just changes it N of to N of negative. So the big thing to recognize is that anytime you want probabilities about a stock being in the money or out of the money, it's always in terms of D2 hat. Okay, and it's either D2 or negative D2, depending on if you're in the money for a call or in the money for a put, right? They'd just be complements of each other. Now, when it comes to expected values, there's a, well, we actually had this formula earlier. That's the one I said, oh, I think it's good to memorize that. It's the same thing again, current price times e to the alpha minus delta t. So that's that. But now we're going to need that because if ever I wanted a conditional expected value, so the expected value of the stock, if you know the stock is in the money for a call or something, what do I do here? Well, remember for like conditionals back in P, whenever you had a conditional, you basically kind of almost on every single problem, unless it was just something you could immediately see, but you basically always divided by the probability of the condition, always. That's always what conditionals were, right? So we're going to actually divide by the probability of the condition. What's the probability of the condition? Oh, well, that's stock greater than, oh, that's the D2 hat thing. So I'm going to do N of D2 hat here on the bottom. And the amazing part is that it's actually the conditional expected value is the full expected value, but sort of like tweaked by this fraction. And the fraction has the probability in the bottom, and in the top is the thing with D1s instead of D2s, but it reflects exactly the same like symmetry there. Right now, this is actually a very difficult thing to see. It's actually crazy that it even works. Because if you think about how you'd find the expected values, you'd have to do like an integral of like X times the probability, the density function and all that. We're dealing with like Lognormal stuff and all. But in a weird way, it becomes like, it magically comes out where the D1 comes into play with the thing with the plus sigma squared over T. And then that's what, like you just multiply by this fraction right here. It's actually a really complicated thing, and it's amazing that it turns out so clean. Okay, but it actually for us, we can kind of use that symmetry to our advantage. And so then if I had maybe the expected stock price, if the stock was lower than K, okay, great. I'm going to have the full expected value, but then I'm going to divide by the condition. And here, since it's less than K, it's a negative D2 hat. And so then the numerator would be a minus D1 hat. And again, it's not something you can rederive. These will be things just to memorize. I'm not a big memorizer, but this is it. But actually the symmetry helps it to be easier. Okay, now, so let's kind of do an example with these and with the D1s and D2s and all that. And so, okay, so we've got here stock XYZ, and I mainly put this on here because I wanted you to see how they might phrase things. So expected value of the time T prices that are above the current price. is 20% more than its expected time t price. Okay, what are they saying here? They're saying expected value of, well, the time t prices that are above the current price. So they're putting a condition, a stipulation on what prices they're actually talking about. So this is actually conditional that ST is more than the current price. Okay, and then that they said here that this is actually 20% more than the expected. So I guess 1.2 expected time t price. And similarly, the other one here, expected value of the time t prices that are below the current price. And again, it's conditional, even though they didn't say the words given or conditional or anything, but because they're putting a condition on it, they're restricting your attention to just some of the values. That's conditional. Expected value of ST, if ST is below the current price, well, that's just 65% of the expected time t price. So this is 0.65 expected value of ST. Okay, so that's what they give us. And then they said they want the total rate of appreciation over the T years, not the annual one. So rate of appreciation, what was that? That was alpha minus delta, but they wanted it over the T years. So I guess they're really looking for this quantity here, alpha minus delta T. Okay, no problem. All right, but other than that, they don't tell us anything. So now we got to figure out what to do here. But okay, well, we can go back to those formulas for the conditional expected values where I'm like, oh, okay, if it's the expected value of stock price given, stock is more or less than some number, it's just going to be the full expected value, but then tweaked by that N of D1 and D2 thing. So instead of writing it all out, I'm just going to say it's the full expected value times. And for here, oh, this is actually S greater than ST greater than a value. So that's actually D2 hat. And on top then would be D1 hat. And they said this is equal to 1.2 expected value of the stock price. And actually that's nice because then that'll cancel from both sides. And I get that N of D1 hat is just going to be multiply the N of D2 hat to the other side, 1.2 N of D2 hat. Okay, well, that feels useful. Maybe I could do something with there. I can't just like N inverse now though, because I actually don't know what this is. And I got this 1.2 in the way. If the 1.2 wasn't there, then yeah, I could actually just N inverse both sides and just get that D1 hat equals D2 hat. But the 1.2 is in the way. And same thing with for the green, I'll kind of do the same thing. It's the full expected value tweaked because it's conditional, and I just have the probability on the bottom, which is again a D2 thing, but negative D2 hat because it's the stock price being below the strike, which your current price, it's kind of acting like the strike. And then on the top, it'll just be exactly the same shape, but with D1 hat. And then this equals 0.65 expected value of ST. And same sort of thing that happens last time. I can just cancel those out. And I get here that N of negative D1 hat is 0.65 N of negative D2 hat. All right, well, good. Okay, well, this actually feels like I got, well, 2 equations and 2 unknowns. I feel like I can do something with this. So what can I do here? Well, how are these related? Well, N of negative is just 1 minus N of positive. So I can actually do that here. 1 minus N of positive D1 hat. So kind of thinking back like, oh yeah, the N of negative is just the complement. So I could do that, and then 0.65 times 1 minus N of positive D2 hat. So that's nice. And now I can substitute in the blue equation into there. And this gives me 1 minus 1.2 N of D2 hat is 0.65. Maybe I'll kind of distribute it out right while I'm here. Minus 0.65 N of D2 hat. All right, then what can I do? I guess I maybe move the 1.2 over to the right side and maybe the 0.65 to the left. So the 1 minus 0.65, that gives me 0.35. Then if I had a positive 1.2 minus a 0.65, that gives me 0.55. And sweet, I was able to get here that n of d2 hat is 0.35 over 0.55. Which is 0.63636363. I'll store that into X. I don't know if I'll need it, but I feel like that's kind of a good one to know. And the cool part then is, well, actually, I know also then n of d1 hat. I don't know if that's going to help or not, but n of, so I'm going to put that in blue here. So back to the blue equation, n of d1 hat is just going to be 1.2 times that. So 1.2 times, and I'll have like X with the box around it. So times 1.2. And I'll store that into Y, but 0.763636363, so I'll round it to like 0.4, but at any rate, that is, I'll put that in for Y. All right, now, how does this help me here? And again, I'm looking for alpha minus delta T. I think about the N of D1 and D2 hats, and kind of thinking back to the D1 and D2. If I knew D1 and D2 hats, at least I kind of see this whole alpha minus delta times T in there somewhere. So I feel like I've got a chance if that's the case. I don't know how it's all going to work out, but maybe I should do that. Maybe I should find D1 and D2 by themselves. So let me find D1 and D2. D1 hat is going to be, so I guess that would be like this equation with the Y down here. So I'd want to N inverse both sides, and that'll give me that D1 hat is N inverse of Y. And we can do that on the calculator on that online. And I got 0.71806. And I'm going to do the same thing with D2 hat. It's just going to be N inverse of like that X. And I got 0.34875. So those are what you get there in the from the calculator there. The online calculator, the normal calculator, if you did N inverses.
When you put it in, did you put like point? Oh, that's D2. Never mind.
No problem. Yeah, it's the N inverse. And the cool part is when you look here, you kind of think like, oh yeah, I'd want to undo the, so I'd have to N inverse. And so I N inverse, you can kind of like, it sort of helps, the equation kind of helps you with that. But yeah, good question. All right, now what do I want to do with these? Well, we actually, you might remember like, oh, D2 is just D1 minus sigma squared to T. But yeah, I mean, actually, that's kind of what's happening here. In fact, if I just sort of took the difference here, D1 minus D2, I mean, all the stuff they have in common would kind of go away. And I would end up with this minus that. So really plus this. So you don't have to mark this up on yours. But so I really actually have, if you looked at it, it would be a full sigma squared T over sigma square roots of T. And actually that's D1 minus D2 hat is just sigma square roots of T. So we usually do D2 is D1 minus sigma squared roots of T, but there are differences that this is sometimes helpful to know that the difference in the D's is the sigma squared roots of T, which is logical from maybe what you've remembered anyway. But because we have D1 and D2, that's going to be really helpful here. D1 hat minus D2 hat. So if I take the 0.71 minus the 0.34 number, we get 0.36931. I'm going to store that into Z here. And the nice part is that, what is that? That number is sigma square roots of T. So this is equal to sigma square roots of t, because d1 minus d2 is that sigma square roots of t. Really nice. Okay, now how's that going to help me? Well, one last little leg here, and I'm almost there, because now that I know sigma square roots of t, I can kind of plug that back into either one of these and get my answer. I can solve for this alpha minus delta times t, whether it's d1 or d2. So I don't know, d1 kind of seems a little bit nicer, so we'll just kind of go with d1. So let me go back up to d1 here. So 0.71806 is equal to, that's my d1 hat, and that was log of S current price over K. And what was the K in this example? Actually, K is also S0. So that's nice. Plus alpha minus delta plus 1/2, well, sigma squared T over sigma square roots of T. So what can we do here? Well, I guess we could kind of pull apart this thing and just have alpha minus delta times T, and then I'd have the 1/2 sigma squared T. So that's actually nice. The log of S0 over S0, that's just the log of 1, which is nothing. And I'm going to have plus alpha minus delta T as a quantity. Then plus, well, 1/2 sigma squared T, but that's actually just the square of this, 1/2 times, I guess, our Z value squared, that Z box thing, right? So this is just going to be 1/2 Z squared up there. And then on the bottom, it's just Z. So over here is just Z. So I can actually just solve that. Yeah, it equals that 0.718 number. So I'll multiply by that Z what I have stored in Z, subtract off 1/2 Z squared, and I'll tell you what we get for our answer. Alpha minus delta times T is going to be equal to, and I got 0.19699. So they might have 20% as the volatility, but there you go. Oh, then we have a question. How do we know that the strike is S0? Well, the strike was just yeah, it's just kind of, well, what's the stock relative to for our example? And so we used K, K was the S0 in this case. So yeah, good question about that. All right. Oh, please. Yeah.
Why is the numerator S0? Why should it be ST?
I'm sorry. Why should what be ST?
Why the natural log, in the natural log, the numerator is S0. Shouldn't it be ST?
Okay. Oh, so here is kind of coming back to here. So it's going to be the log of S0 over K, and the K was also S0. So yeah, it feels like it. It's not actually this. That's not what we're having. But yeah, good observation. Yeah, sometimes it feels like we should have ST over S0, right? That's good. It's good that you're training your mind for that. That's good. But in this case, yeah, it's just S over K. So good. Kind of like Black-Scholes. Yeah, great. Excellent. Great question. All right, now, okay, just a couple more things that I wanted to talk about today. Okay, so here's one. This is, sometimes they'll ask us two different questions that feel very similar. Okay, and sometimes they're actually not very easy to do. So here's one that looks pretty innocent, but it's actually quite a bit of work to get there. However, I want to show you something really interesting with it all. But okay, so it says here, give an expression for an expected payoff of a T-year put on a stock with strike K, then assume the prices are log normally distributed. Okay, so, well, we want the expected payoff. So we want expected payoff. But we know that the payoff for a put, it kind of depends, doesn't it? It's either 0 or K minus S, and it's 0 if S is more than K, and K minus S if S is less than K, right? But the thing is well, I can't just plug something in here. It sort of depends. So back to exam P, there was a way that we could actually split a probability into cases, right? That's really what we did. It was called the law of total probability. And we would say the probability of A is the probability of A if I'm in case one times the probability of case one. Do you remember this? The law of total is kind of like the denominator and Bayes theorem and stuff like that. So yeah, totally. So this is actually what we're doing. But the cool part is that there's a corresponding equation with expected values. And if I had expected value and I kind of wanted to split it into cases, I could do that. And I could have that the expected value of X is the expected value of X if I'm in one case times the probability of being in that case, plus the expected value of X if I'm in the next case times the probability of that case or bracket or situation or whatever. In other words, but I'd have to make sure to cover all the cases and there couldn't be any overlaps because I can't double count stuff and stuff. So that was the only stipulation, but we actually used that quite a bit back in P, at least the probability one. The expected value one, I wish they would have taught better, but they didn't, but that's okay. But that's what we're going to use here. I want the expected payoff, but I know the payoff if the stock price is below K or if it's more than K. So this is a perfect situation to use this expected value. So I'm just going to simply write expected payoff if the stock price is less than K. Oh, sorry, capital T's we're using here, I guess, times the probability of that case, ST less than K, plus expected payoff if the stock price is more than K times the probability of more than K, or greater than or equal to K, or whatever, however. But so these are the two possibilities. There's no overlaps and it covers everything. Okay. So just simply, that's actually what we're doing here. We're just doing, just doing those. And sorry, this is a bracket or a straight up and down line, not a parentheses. Apologize about that. Okay, but actually real easy so far. So in this case, what if the stock price is below K? What's the payoff? Oh, now I can actually be more specific. This payoff would be K minus S. And if the stock price is more than K over here, what would be the payoff of this put? And there the payoff is nothing. So the beautiful part is this whole thing over here is really just a nothing. Awesome, we love it. So that's pretty cool because now I've got expected value of K minus ST if ST is less than K times, and we'll probably use the D2 stuff here. So probability ST less than K, so it's always S2 or D2 hats. And so this is just N of, well, since it's stock below it, it's the negative D2 hat. No problem. Okay, now what can we do with this? Well, it's an expected value of a difference, so I can split it into two expected values. So I'm going to have expected value of K if ST is less than K minus expected value of ST if ST is less than K. So I've got all of that times N of negative D2 hat. Okay, and then actually, oh, that first one is actually pretty easy. Expected value of a constant is just the constant. So this is actually just K, right? That's not too bad. And then now this is, oh, this is those conditional expected values we talked about, expected value of a stock price if the stock price is less than K. Okay, well, that's actually just the full expected value. So here I'll just kind of write it out, S0 e to the alpha minus delta T. But then tweaked because it's conditional. So I'm going to have to divide by the condition. And since it's S less than K, then it's the negative D2 hat. And the top will be the same thing, but with D1. So minus D1 hat. And then all that's going to be times N of negative D2 hat. Okay. And so I guess I can kind of distribute that N of D2, negative D2 hat in there. So I've got K e to the negative, oops, sorry, K N of negative D2 hat minus, and then I guess the N D2 hats are just going to cancel here. So S0 e to the alpha minus delta T N of negative D1 hat. Okay, so a little ugly, but I've seen them actually ask this on questions where they just said like, oh, I've got this put, what's the expected payoff in a year? And to actually do that, you'd have to go through this process. This would be what you do. Okay. And it's just all about probabilities, true probabilities, and we're good. But I wanted to show you this thing here where if the payoff depends on kind of like what the stock price is, you have to split it like this. And it's a little bit weird to do, but it's actually very reasonable for them to ask on the test. Now we're going to do something even cooler with that in a minute, but we'll get back to that in a sec. Okay. So let's talk about risk neutral pricing. So I promised that was a huge deal, and this is basically a review slide from the other day. But risk neutral pricing, what is it? What did we care? Well, we dealt with it with like binomial trees, which was what, yesterday, I think? Yeah, so yesterday. And well, we thought of the risk neutral universe as like this really boring universe where every rate of return, every rate of return is R, the risk-free rate, right? So every stock, every call, every put, every stock squared, everything, every max, every min, everything grows at a rate of R. So every expected return is R. Super boring, but that's okay. And then we use the star when we're talking about it. So, okay, that's fine. So we just kind of review. And so then in order to price something, if we wanted to find the price, do you remember what we did? Well, we found the risk neutral expected payoff, and then we discounted with R. So the price was always equal to e to the negative RT times risk neutral expected value of the payoff. Now, two special risk neutral quantities were actually pretty interesting. Just the risk neutral expected payoff is actually the forward price. And we remember that the forward and prepaid forward were just through interest. So actually this is the prepaid forward. If I just took the risk neutral expected payoff and discounted it back. But that makes sense because you're basically saying like, oh, okay, well, if I wanted to know how much something like the equivalent price now to pay to get something later, we call that the price, but we're actually doing the risk neutral pricing. We're taking the risk neutral expected payoff, bringing it back. And this is why the prepaid forward is so critically important, because it just, it's actually the same as the price, but it's kind of how we move things back in time if they're not really clear. Okay. And in this case, by the way, it would actually be the risk neutral expected payoff of one share of stock. And do you remember what the expected payoff of a share of stock was? Well, that was that formula. If we go back several pages here, back to this one, we said, oh, okay, well, the expected value is this. So what would change if I made it the risk neutral expected payoff? And here we go back to the idea like, oh, what's risk neutral universe anyway? Oh, every expected return is R. So actually that would just mean this, R minus delta. But notice that is actually the forward price. The forward price is SE to the R minus delta T. Pretty awesome. And the prepaid forward would just be that e to the negative RT times e to the negative RT, and the R would go away, and I just get SE to the negative delta T. So pretty neat. Yeah, it's pretty awesome. Now we're going to do it. Actually, we're going to apply this to the previous page of where we just were. So we were right here, risk neutral pricing. Sorry about that. Now we're going to kind of go back here. And what if I wanted to actually find the price of this thing? Okay, so what if I wanted to do, well, e to the negative RT times the risk neutral expected payoff? What would change here? And interestingly, it's just going to change things real simple. It's not going to change a lot. It's just going to kind of almost be like a notation thing only. So if I did, then I would need the risk neutral expected pay. Oh, so e to the negative RT here, risk neutral expected payoff times the risk neutral probability, risk neutral expected payoff, risk neutral probability, right? So I need all that. But again, I would still get a 0 for that second thing, so that's gone. So I still need e to the negative RT, risk neutral expected payoff here. And then, okay, what's going to happen to this one? Well, since it's a risk neutral like probability, the alphas become R's. So what did that mean about D2? Well, that means that D2 hat here. Well, if I replaced alpha with R, if I wanted to do this risk neutrally, I'd have to change that to an R. But that's actually what they call just regular D. Regular D is just if I had R there instead of alpha. D2 hat is if I have the alpha. So if I want real probabilities, I keep the alphas, but if I want price, I need risk neutral, so I need R's. And so basically for us, that means it's just going to change, oops, it's just going to change this D, it's just now going to be a negative D2, straight up. And then, okay, what's going to change here? Well, I still got this e to the negative RT here, so I got to kind of put that everywhere now. This is risk neutral here. So the D2 hat still becomes a D2 again. All right, e to the negative RT. So expected value of K is still K. Here though, the risk neutral expected value, every alpha turns into an R. So this actually becomes R minus delta. These hats go away because it's all risk neutral. And so I got e to the negative RT times, and then all this, basically all the same stuff is going to happen. I'm just going to have negative D2. I'm going to have an R here and a negative D1 here, which gives me KE to the negative RT n of negative D2 minus, okay, and then I've got e to the negative RT times this, so that positive RT in the exponent is going to be combined with the negative RT on the outside, so it's just going to go away. Then I get S0 e to the negative delta T n of negative D1. But that should look familiar, right? This is the price of a put. Right, this is what Black-Scholes did. This is all the Black-Scholes did and why they became so famous for it. They just did this risk neutral expected payoff, discounted back, so they found the price of a put because they know like, oh, each put is going to pay this. So what's the expected, the risk neutral expected payoff, discounted back, we call that the price. They called that the Black-Scholes formula. KE to the negative RT n of negative D2 minus the prepaid for of S n of negative D1, and you got it. Okay. So it's pretty neat, right? It's pretty amazing. That's where they came up with this. But it's a good practice for us to do that. Actually changing things to risk neutral is actually pretty easy. Okay. And in fact, we've just got a couple of more problems here where we're going to be able to sort of practice this, Black-Scholes, and kind of how we would handle these problems. Okay. So, okay, so here's one. So a stock price has the current stock has a current price of 60. Its expected return is 12%. So S0 is 60. Alpha is 0.12. Continuous dividends. Okay, so delta is 0.02. Volatility, sigma, is 0.2. And a Sharpe ratio. Ooh, okay, Sharpe ratio. Okay, what was the Sharpe ratio? Oh, that was alpha minus R over sigma. Okay. Now, if you think about it, this is like the expected return over the risk-free rate. So that's the risk premium, they call that, but normalized by the standard deviation. So that's what they call the Sharpe ratio. But so, okay, I guess I'm not sure what I'm going to need to do with that, but I mean, I have everything but R, so I guess I could solve for R if I needed. But all right, we'll come back to that. assuming the stock price has a log normal distribution, determine the price of a derivative security that has a time for value of the sum of the square and the cube of the stock price at that time. All right, so here's what we're going to do. We're going to introduce something that we're going to do a lot more in our last seminar, which is sort of like a two-stage pricing way of pricing things. What we're going to do is we're going to first write what would be the value at that time, basically the payoff. In this case, we could just call it that if we want, but what's the value at that time? And then bring it back. Okay, so the value at time 4. So if you, in fact, you know what, maybe I'll just call it the payoff. Payoff is going to be, well, the time for price squared plus the time for price cubed. That's just what they said. And so if I want the price, I would have to do the, well, the risk neutral pricing. So I'm going to have to find the risk neutral expected payoff and then discount it with interest. So I'm going to have e to the negative r times 4. And then the risk neutral expected payoff here. Okay. So I guess since I'm going to be doing everything risk neutral, I'm going to need R instead of alphas. So I'm going to need R's everywhere, but actually it's a real easy fix. And then I can use this to solve for R. So let me just do that real quick. 0.035 is alpha, so 0.12 minus R, the thing I'm looking for, over sigma 0.2. Okay, that doesn't seem that hard. So what do I have here? So multiplied over 0.035 times 0.2, then take 12 minus that. Oh, sorry, 0.3, sorry, 0.35, not 0.035. That's not good. 0.35. Okay, and what does that give us now? 0.35 times 0.2, and then 12 minus that number. So I guess I have 5% for the continuous rate. Okay, the continuous risk-free rate, no problem. All right, now how can we combine this with the things that we've done before? Okay, so they're really asking me about stock 4 price, right? Time 4. So I want to know the distribution of log of S4 over S0. And I know that that's normally distributed of alpha minus delta minus sigma squared over 2 times 4, sigma squared times 4. Right, so no problem there. But now, because I'm going to have to do things risk neutrally, I really need like the risk neutral version of this, because all these risk neutral, everything now has to be risk neutral. So that's okay. So maybe I'll just kind of denote it like maybe N star. But what's the only thing that's going to change here? Super easy. That alpha will just become an R. Easy. So I've got here that this is going to be sort of like the risk neutral normal. You kind of think of it like that, right? Of R minus delta. So 0.05 minus 0.02 minus 0.2 squared over 2 times 4. Then 0.2 squared times 4. So this is kind of like a risk neutral normal of, okay, 0.05 minus 0.02 minus 0.2 squared over 2 times 4. So notice how 4 years worth of growth is really small. Sometimes it might even be negative if you do risk neutral. It's totally fine. It is what it is. So 0.2 squared times 4 is 0.16. All right, okay, so now this is beautiful because now this tells me log of S4 over S0 as a risk neutral normal is just, yeah, normally distributed with mean 0.04 and standard or variance of 0.16. So that's great because I'm going to need that here. And actually, since I have my 5%, I might plug this in here now to e to the negative 0.05 times 4. Risk neutral expected value of S4 squared plus S4 cubed. So I'm going to need to know what is, so if I solve for S4, what do I get? And my S4 is, so basically back to what we were doing before, Nothing's different because it's an N star. It's normal. So it's just that. It's just in a different context, but no problem. So I can E both sides, multiply by S0. S0 was 60. E to this N star of 0.04 and 0.16. So what do I have here? All right, this is going to be E to the negative, well, 0.05 times, so 0.2. And then risk neutral expected value of, okay, now S4 squared, what's that going to be? 60 squared, E to the, so I'm squaring this now, so 60 squared, and then E to the 2 normals, right? Is that what we did? So 2 normals, 0.04, 0.16. Plus S cubed, so that's going to be, I guess, 60 cubed, E to the 3 normals now. So 3 N star, 0.04, 0.16. All right, so actually same thing I've done before. I'm going to just distribute the 2 in, I'm going to square it, I'm going to substitute the 3 in and square it. So let me just kind of see what I get there. So this is going to be E to the negative 0.2. Risk neutral expected value of 60 squared, E to the, okay, well, 2 times 0.04 is 0.08. And then 2 squared, 4 times 0.16 is what, 0.64. And then 60 cubed, E to the, well, okay, 3 times 0.04, which, so N star of 0.12. And 3 squared times 16. So 3 squared times 0.16 is 1.44. And you might get some big numbers there, but that's okay. It's 144% volatility, which is pretty crazy, but okay, whatever. It is what it is. But actually, now that we have that, it's easily finished because I could do E to the negative 0.02 or 0.2 times, all right, now I can do the expected value. So I'm gonna have 60 squared expected value, E to a normal, since everything's risk neutral, it's good to go. E to the first parameter plus 1/2 second parameter. And then 60 cubed times E to the, well, expected value, E to a normal, E to the first parameter, 0.12. Plus 1/2 the second parameter. Okay, and for sake of time, I'll just show you what I got here was 414,037. But again, the final answer is not really the important part. The process is the thing. But actually, right, doable. But we're able to do this amazing thing now with just that one more additional piece of information that, like, oh yeah, risk neutral pricing, just alphas become R's. And I just do the exact same process again, even though this is a really crazy looking problem, but we actually did it super easy. Great job. All right. Okay, then I just kind of wanted to talk about Black-Scholes just for two problems here, but just some non-traditional problems that you know how to do for calls and puts and all that. So I wanted to do a currency one, but I also wanted to do an exchange option. So I wanted to do one more of those here, but to do that, I just want to talk about a slightly more general version of the Black-Scholes formula. So this is the one that you probably use all the time, which is great. I think it's better to remember a slightly different one though. So the one I think is better to remember is, well, this is prepaid forward on S, and this is prepaid forward on K. So if you ever have things that aren't like a stock and strike, but maybe 2 stocks or currencies or whatever, then it's really just, it kind of feels a lot like the put call parity, where I'm just going to do prepaid forward of the first thing, but now times N of D1 minus the prepaid forward of the second thing times N of D2. Right? If it was put call parity, it would just be call minus put is, and then forget about the N of D1 and N of D2, right? That's actually put call parity. Great. It's actually, in fact, the Black-Scholes tells you how you should split apart put call parity to get just the call and just the put. so it's actually really nice. But the reason I like this is because, well, it's actually good for a computational point of view too. Because what I'll do is I'll actually compute this out, put this in for X, and I'll compute this out, put it in for Y. And then actually it turns out that the formula for D1, and you can check this out later, but it actually becomes log of X over Y. But then that takes into account all the R's and the deltas and stuff. So you actually just have plus 1/2 sigma squared T. Right, because that's where the R's and the deltas come from anyway, was from the stock and the strike or whatever, right? So when you do the prepaid forward as a whole and put it in, now this might be a little new and you might be a little nervous to do it, but it's actually a lot cleaner, and we'll see it here in a minute. But it's really nice because you're going to have to compute this out anyway. So in order to find out the D1, you kind of have to do half of that computation in the first place. So if you kind of do those, put them in for X and Y, compute out D1, D2, do the, the normal distribution and stuff. Then when you go back to compute it out, you'll have to put in the N of D1 and N of D2, but you already got X and Y. So you can just do X times the one probability minus Y times the other one, and you get your answer quicker. And because we do these so many of these, any little bit can really help us. So if it's ever like, yeah, I feel like this is just kind of a good one from an efficiency point of view, but also it's good to be more general, because what if your stock has like discrete dividends? Then what do you like actually do here? Like we're not really sure. Okay, so we're going to see that in our next example. It's an exchange option, and one of the stocks has discrete dividends and one has continuous. So we assume that both of these are log normally distributed, and okay, for a stock, we've got the current price is 100, alpha is okay, got it. So we've got all these stats for this one. Stock Y, you've got this dividend of 4.5, okay, in 1.5 years. Current price is 60. And now they tell us the correlation. So correlation between them is a -0.4. Okay, and the risk-free rate is 5%. All right. Determine the price of the option that allows you to exchange 1 share of X for two shares of Y. Okay, now remember what we thought. The shortcut we could say is exchange means to give. So I'm going to exchange money for coffee. I'm going to give away my money for the coffee. So we're going to actually give that to receive this. And we could write it as a call or a put, but let's write it as a call. So a call, we're going to call something to us. What was it? Oh, I guess 2 shares of Y. And we're going to have 1 share of X in 2 years. If we thought about it as a put, we could just exchange the X and the 2Y, like switch those around, and that would be as a put. But since we're doing Black-Scholes, it kind of calls are just nicer anyway, right? So, okay. But just, we got to get those in the right order though, otherwise we get the problem wrong. So, but actually super easy from here, because now we're just going to use that general version. So I'm going to do the prepaid forward of 2 Ys times N of D1 minus the prepaid forward of X times N of D2. Super nice. Okay, so what's the prepaid forward on 2 Ys? Okay, well, that one is going to be 2 times. Oh, okay, well, it's a stock with discrete dividends. So I'm going to do current price minus the present value of the dividend. So 450 e to the negative 5% for 1.5 years. So 0.05 times 1.5. And okay, just for sake of time, I'll give you what these values are, but compute that out, you get 111.65. So I'm going to store that into X. Okay, and then the prepaid forward on X, okay, well, X is continuous dividends, so that's great. So that's just going to be current price e to the negative delta 0.03 times 2. Okay. And I'll give you the price of that. That was 97.176. So I'm going to store that into y. Okay. All right, what do we do now? Okay, well, actually now we need D1 and D2. So how are we going to get D1 and D2? Let's find D1. So for D1, I'm just going to do log of x over y plus 1/2 sigma squared times 2 over sigma square roots of 2. Now the only thing I have left to do is to find out, well, what is sigma? And for sigma, it's actually a formula that we need to remember, but we can always think of it as what we would do if we subtracted two variances, because that's actually what's happening here. We're actually doing a variance of something minus something else. So it's actually better to do the variance first. And if I did a variance of x minus y, it's going to be variance of x plus variance of y minus 2 covariance of x and y. So you might see in the formula, you might remember that it's actually sigma x squared plus sigma y squared minus 2 rho negative 0.4 sigma x sigma y. Okay, now we don't have enough time here, but we are actually doing an x for 2 y's, but yet actually it doesn't become like a 4. Okay, so don't worry about that. And the reason is because we're not actually doing x and y. We're actually doing like log x and log of 2y. That's actually what we're doing. And the log of 2y becomes a log of 2 plus a log of y. And the log of 2 just kind of goes out of there anyway. Okay, but that's the reason why you kind of don't like double the y thing. It's always just x minus y. Kind of think of it like that. That helps us to know the formula here. And they gave me the sigma x and the sigma y. So the value we get ultimately there is 0.1425, which means that the sigma is square root of that, which is 377 something. I would store that into z. And then I would actually just put that in here. So that'll be my z. So I'll have z squared there and a z there. All right, but at any rate, without too much here. So this was actually then 58574. And then once you have that, great. Then you can get your probabilities and you can kind of finish off the problem. I'll let you do that. The final answer was 31,459. Okay. Right, and then and then there was a question here is like, when do you use d hat and when do you do just a regular d? And so the answer is that that's always actually a big question. And so that gets back to, well, are you doing risk neutral pricing or are you just doing like the regular whatever? Okay, so if you're doing risk neutral pricing, in other words, if you want to find the price of something, you're going to have to do risk neutral. So you're going to need the D's to bring things back and the R's and all that. If you just wanted to find the value in the future, if there wasn't anything about the current price of like some kind of combination of stuff, if you just wanted like some expected payoff or the price of the stock in a year or like some probability about the stock in a year, you're not doing pricing back at 0. So for that, you just use all the regular probabilities. Like you might think back to maybe some of the early questions that we did today, like these. You're just like, oh, okay, I just wanted to know what's the probability that the price is going to be, in 2 years, going to be between 105 and 110. We didn't do risk neutral there because we're not trying to find like the current price of something. We're just doing some calculations in there and finding out stuff about things in the future. But this, when we do questions about trying to find the price now of something crazy, we're always going to have risk neutral. We're always going to use R's instead of alphas. And that's why you go about those. So great question. All right, last one here. so hopefully you got a chance to look over this one, but all right.
One
okay.
second before you move on.
Oh yeah, what's up? Yeah, please.
Can you go back to the previous slide? For a
Oh,
second?
absolutely.
Okay,
Yeah,
so right now we found D1, right?
great.
And
Good.
then so we have to find D2 with like D2 is 1 minus D1, right?
Good. Well, D1 minus sigma square roots of T. So that would be like, so it's always like, yeah, D2 is D1 minus, so sigma, which we had for Z there, square roots of 2. So that would be that one.
And then we just plug this back into
Yeah, then you
the
get N of D1
previous.
and N of D2.
Oh, get ND1 and D2,
Yeah,
but then plug
good,
that.
good.
Okay, all right. I think I got it.
Perfect, good. Yeah, and try finishing it off later. But yeah,
I'm
you've got
gonna-
all the pieces there. Perfect. In fact, I'll just tell you what these probabilities are. I got 0.72097. And for N of D2, I got 52069.
You know what? Yeah, let me.
Yeah, see if you're on the right track later. So yeah, no, thank you so much. Yeah, please.
Yeah. All right. I will make sure I go back and do this because yeah. Okay.
Perfect. Yeah, great. Good. All right. Okay, and then last thing here. Okay, so it's a currency one. So just want to kind of do one of these here. And again, we'll, as long as we get it set up the right way, we can kind of cut to the chase a little bit. But all right, a few years ago, Asher made an investment in Thailand. So 2 years from now, he'd like to withdraw 600,000 Thai bahts from the investment, transfer it to his account in Australia. Payable in Australian money, whatever that is. Okay. Currently, 25 bahts equals $1 Australian. So maybe I'll just call it A for that, or you could just put $sign if you want. The risk-free rate is 5%. So RA is 0.05. Then R baht is 0.06. Then the volatility of the exchange rate, so sigma is 0.3. Okay, no problem. And so he'd like to guarantee that his investment will bring him at least 25,000 Australian dollars now. So worried that the exchange rate will be unfavorable, he decides to purchase an option to guarantee the exchange rate will be sufficient. Determine the price of this option in Australian dollars. Okay. All right, so 2 years from now, he'd like to make sure that he withdraws. So this is a 2-year option. And we just need to know, well, is this a call or a put? So get your voting fingers ready there. So we know that the price is in Australian dollars. So we know that it's going to have to be denoted in Australian, which means that it's going to be baht and Australian in 2 years. And we can actually say what he's exchanging. I guess they're exchanging 600,000 baht for 25,000 Australian. All right, that's kind of the thing that we're trying to make sure happens here. And the big question is a put or a call. Okay, so call or a put. What are we after here? So think about what you think here. And you can think about it one of the two ways. What's he worried about? Is he worried about the 600,000 being less than this or more than that? Or do we want an option to buy the 600,000 baht or to sell the 600,000 baht? So think about either one of those and kind of write down what you're thinking, call or put. Okay. And we'll start with the easier of the two, the whole option to buy or option to sell. So if you think about it, he made the investment. He actually has the money. He just wants to sell it into his money. He has it. He just kind of wants to liquidate it so that he can get his money for it. So this is an option to sell. This would be a put. But the other way to think about it is you can think, well, what's he worried about? So what's he worried about? Well, okay, so he's got his money here. You know, he just wants to make sure that he's going to get 25,000. So what's he worried about as far as the 600,000 bahts? and the 25,000 Australian. Well, what are we worried about? Well, I guess he's worried that, well, that he's not going to be able to get enough from here, that value is going to go down. It's not going to be enough to give him 25,000 Australian. So he's worried that that is going to be below 25,000 Australian. If you were to convert it, maybe it'd only be like 24,000 or something. So he's worried about that. That's kind of like my stock price. So I'm worried that the stock price is going to go below the strike. So what kind of option pays if the stock goes below the strike? Ah, that's a put. So that's the other way to think about it. But now that we have that, no problem. So now that we know it's a put, we're going to do, Black-Scholes on this. So it's going to be the prepaid forward on the 600,000 bots times n of, negative prepaid forward. I like to do it like that, sorry, with the D1s first and D2 second. So negative prepaid forward of the first thing times n of negative D1 plus the prepaid forward of the second thing, 25,000 Australians times n of negative D2. And I just think like, oh, okay, what's my currency here? My currency is Australian. So when I do this 600,000 bots, I will discount it by the bot rate because that's what it is. So 0.06 times 2, but I've got to convert it because it's got to be all in Australian. So I'm going to have to get rid of the bots, put in the Australian. And so, well, I'm going to have to use the current rate to do that. 25 bots is 1 Australian. So that's cool. Just kind of get that there. So n of negative D1. Then plus the prepaid forward of 25,000 Australian. So 25,000 Australian already is Australian. So I don't need to worry about that. E to the negative 0.05 times 2. N of negative D2. And so then, yeah, I'm just going to kind of now do my X and my Y thing. So I'll put this in. I'm not going to put the negatives in there, but I'll put just all that. So I'm going to put that in for X, and I'll put this in for Y. And just so that you have the numbers, I'll show you. So the numbers were 21,000 to 286. Sorry, so something like that. I can't even read my own writing. Sorry about that. So 21,200 and something. Then here, this was 22,620 or so, something like that. But for me, I'm going to get my D1. I'll say D1 is just log of X over Y plus 1/2 sigma squared, so 0.3 squared times 2 over 0.3 square roots of 2. And I got there 0.06877. And once we have that, we can get D2. D2 is D1 minus the denominator, right? Minus sigma square roots of T. So we can get D2 pretty easy. And to make a long story short here, the final answer turns out to be 4392.70. And 70 what? Australian or baht? You can always say, look back here, it's going to be that many Australians. Okay. All right. Well, we did it. We finished. All right. Took a little longer again, but that's okay. I'd rather give you guys a little bit more time than less, but anyway. All right. But anyway, I hope that helps out. It's just Black-Scholes again, and try this out. See if you like this method better with the X and the Y. You could do either. Sometimes the one is better, sometimes the other, but just kind of in more general and just for computational reason, I like this. But anyway, well, thanks so much for joining, and I hope you guys have a great week, and I'll see you guys on Saturday. Okay.